Test, test. 1, 2, 1, 2. Test. Is that it? 1, 2, 3. That's as far as I can count. One, two, 1, 2. Test, test. Yep, okay. Yeah, okay. Okay, I think it's going to be time to start. Welcome everyone, thank you for joining. This is going to be the first talk of the first day of the Embedded Linux conference. And I am already going to start to fill your brain with a lot of Ethernet driver information. So I'm Maxime. I've been working at Bootlin for the past 6 years now. And in my job, I've been mostly working with Linux drivers for Ethernet controllers, Ethernet PHY controllers, switches, and so on. And today, I'm going to talk about what's inside an Ethernet driver. When we talk about Ethernet, it's something that we see a lot nowadays on embedded devices. And an Ethernet controller is not something that is considered as simple. It's going to be in charge of course, sending and receiving data, but you can do much more with that. And in the end, when you write a driver for that, you'll end up having to interact with a lot of various infrastructures within the kernel in order to configure a lot of the different possibilities that your hardware can offer. So the goal of this talk today is to kind of take a tour together of what you find in such a driver. It will help you as a user, as a developer, if you want to learn more about what's inside and how to configure everything, how to debug maybe. You are going to maybe see something that looks familiar if you have already written such a driver, but hopefully you will learn one thing or two. I will tend to focus on what we find specifically in embedded systems. There is nothing really specific about embedded Ethernet drivers. Maybe besides the fact that you usually find it inside an SoC, so a system on a chip. But everything that we're going to see here will still apply for any kind of Ethernet controller. It can be like a PCI card that you're going to plug in your computer. It can be a network controller for some data center machines that go really fast, whereas usually in embedded systems we go a bit slower than that, but all what we can see can still apply here. So let's first take a look at what's inside a typical Ethernet controller. So this is a very, very simplified view of what you find in there. So in your Ethernet controller, you have, first of all, in the middle, it's a MAC. I don't know if you can see my pointer. The MAC is really about the 802.3 standard, so the Ethernet part of sending and receiving frames. So the frame will have a dedicated size. That's called the MTU. When you start sending a frame, you need to start to send a bit of special data before actually sending your actual payload. That's called the start of frame. You need to deal maybe with collision if you have a half-duplex link, and maybe do a bit of flow control in order to make sure that the device you are talking to, that's often referred to as the link partner, is capable of receiving what you want to send, or maybe you need to slow down a little bit or stop transmitting for a while for the device on the other end to keep up with the pace. The MAC is also in charge of making sure the link stays established, so sending what's called an idle word on the link to make sure that the link is reported as active on both sides of your cable, basically. So that's really the heart of your Ethernet controller, but there is much more than that. Usually you have queues within your Ethernet controller so that you can queue a packet while one is being sent already, knowing that nowadays we have pretty powerful CPUs and they are capable of generating data much faster than what we can send. So if you have especially a very slow link, like 10 or 100 megabits per second, it can take a while to send the packet, and you might want to keep pushing things in your queue while the other packets are being sent. You of course have interfaces that goes in and out of your controller. So you have one that goes towards the outside world. That's called the MII, Media Independent Interface. Usually it's connected to an Ethernet PHY on embedded devices. But again, I say usually because the PHY can be embedded within your SoC. There can be no PHY at all if you do some fiber, for example. And on the other end of your controller, you have an interface towards the CPU, so your host CPU. It can be through an internal bus on your SoC. It can be through a PCI link. And you will have DMA to do the transfer of data between your controller and your host. So we are going to talk about that. And finally, maybe the most important thing would be everything else that you can find. And this is what makes every controller different. you will find a lot of other engines within your Ethernet controller that can do extra things. You can timestamp your packet when you send and receive them. You can do a bit of filtering at the hardware level in order to drop the traffic that you don't want, or maybe to slow down the pace on the transmit side, or to do the queue management, or to offload some things in the hardware. For example, checksum computation is a good example. In the data you send, you have some checksums at the IP level, at the TCP level, and some hardware can compute these checksums on the fly or check them when you receive your data. So a lot of these engines exist in various hardware, and it makes, in the end, Ethernet devices very configurable. And this is the main idea of this talk. We have lots of things we can configure. How do we do that, and how do we interact with that with the rest of the kernel? So I'm going to focus a lot on the internal kernel structures. I will try not to bore you too much with code, and instead I will try to pinpoint the important structures, the important API bits that you will need to access in order to implement what you want. And I will give a lot of links towards documentation, because in the end it's the most important thing. The backbone of a typical Ethernet driver is going to be the same as for any network controller. You need to provide from your driver a struct net device. That's going to be the backbone of the driver. So you will create it in your probe function for your driver. You will do some initialization of your net device, and at some point you will register it towards the network subsystem. Once you have registered your net device, it will become an interface from the user space point of view. So when you run IP link show, or maybe ifconfig, if you haven't moved away from that tool yet, it will show you interfaces that they have a name and they have an index, the IF index. These are net devices within the kernel. You can have hierarchies within your net devices, so you can actually build trees of net devices. For example, when you create a bridge in Linux, you will have multiple interfaces, and you will bridge them together through another net device. So you have a notion of parent and children interfaces. We call that lower and upper interfaces. You allocate your net device. There are lots of helpers that exist for that. But for Ethernet in particular, there is a variant of the allocation helper that's called the alloc etherdev MQs. It will allow you to allocate your net device for your Ethernet controller with a few extra things that will make them more suitable for an Ethernet net device. For example, you can specify the number of queues you have within your controller. And this function will do the allocation and at the same time allocate all of the resources that are going to be needed to handle these queues. And you also pass a private size. That's going to be the size of the pointer you want to have to keep your what's called private information. So basically everything that's going to be used only by your driver to keep its own context. And you get that with the netdevpriv function. An important thing that I want to stress out with that is once you have called register netdev from your driver, from that point on, it becomes visible to the user. So the user can start configuring it. It might want to start using it right away. So everything must be ready in terms of resource allocation at that time. To continue with this net device, like any other drivers, I don't know how familiar you are with driver development in the kernel, but the way a driver typically works is that you will provide a set of callbacks or operations, and it's going to be basically the entry points of your driver. Your kernel will call into these functions to ask your driver to do something. A typical example is a callback that will be used to transmit a packet. The kernel will ask your driver, can you transmit that to the outside world? In the net device, these are called netdevops, and they are often referred to as NDOs. So if you see in the mailing list some discussion about a new NDO, we are talking about a new operation, a new callback within the netdevops. There is only one that is mandatory, which is the transmit callback called NDO start exmit, basically to ask your driver to send something. Again, these netdevops, they are really generic, so they are in the same set of operation exists for Ethernet devices, but also for Wi-Fi devices, for CAN devices, and so on. They all use the same set of operation, and you are not expected to implement all of them, but at least implement the one that's going to be used to send data outwards. Again, you specify them before you register your device. So now we've seen the important bit, the net device. We are going to start talking about the data path. So how do you send and receive actual data That's one important part of your driver, and it's actually the one thing that we ask you to do in your driver. How do you send and receive things? We are then going to talk about the control plane, so how do we configure the driver. But first, let's see how do we send and receive data. Before we dive into the actual functions that we use to send and receive, one important bit is how do we represent the data that we want to send and receive. Within Linux, we have the notion of an SKB. I don't know if you've ever heard of an SKB before. It's short for socket buf. So it's the data structure that's used in order to store a packet within its traversal of the kernel. So it's created either when you want to send a packet from the user space socket API, so you unqueue some data into a socket from your user space program, and here in the kernel side an SKB will be created, and it will traverse the whole networking stack, going through all of the encapsulation processes, and it will end up at your driver, and your driver will be asked to send that SKB outwards. On the other end, when you receive data, your driver will create the SKB, and it will push it towards the network stack. And the network stack will decapsulate every layer to see who is interested by that data. The internal structure is a bit complex. We have data and metadata. The data, the actual payload that we want to transmit, it's actually handled through 4 pointers. These pointers will point to an area in memory that's going to contain our actual payload. And this payload is stored into the data section here. Well, I cannot even see where I'm pointing here. You have some headroom and tailroom at each side of your actual data. This is because when you want to encapsulate, for example, your traffic, well, you are going to actually take some space within the headroom and turn that into data. You are going to put data in front of your packet. In other cases, you might want to put data at the end if you want to add some kind of a checksum or extra data in the end. And then you have another area that is going to be the shared information that's going to be used by various players within the stack. For example, when you are going to timestamp your packet, you will put that information in there. And then you have other pointers to refer to where are all of the headers from your packet, where is the MAC header, transport header, and so on. But these, you don't really need them in your driver, actually. You just care about the actual payload you want to send or the payload that you just received. So very important part of the hot paths, because this is actually what you're going to send and receive. You create it in your driver with build SKB, and you free it when you no longer need it, especially on the transmit side. Usually the data section is what you are going to map in DMA. So you are going to create a DMA mapping and then create a descriptor for that mapping and then send that into your controller. The same on the receive side. The DMA mapping in itself, in some platforms, can be the bottleneck. So there is a kind of new API that was created that's called page pool. And the page pool API is designed to keep a pool of memory that you need to use for your network traffic for your controller. And it will keep the pages mapped. So we don't use really a granularity of the payload of the data. We use a granularity of a page in the kernel to store the data. And it gives us quite a lot of leeway in order to do the memory management. And it's usually faster because you can do recycling very easily with that. The page pool is a prerequisite if you want to use XDP, which I'm going to talk about a bit later on. So if you want to use XDP in your driver, you need the page pool API to be used. But you can also use page pool without XDP, and usually you will still have some kind of performance improvements. Some documentation can be found in this link. OK, so now let's talk about how you transmit some packet outwards. So I said there is an NDO for that, the start XMIT, and the kernel will call that callback when it will ask your driver to send something. It will pass as a parameter the net device that represents your device and the SKB that you need to send. The typical process for that is that, OK, you will take the SKB, create a DMA mapping, or use the page pool API for that, create a descriptor, and then unqueue that descriptor into the transmit queue for your device. In some cases, you will have multiple transmit queues. We'll see why this is important. And in that case, you have a function that you can call skb get queue mapping to know on which transmit queue do you want to send that. Because the decision of on which queue your skb should be put is going to be done by the kernel, or in some cases by user space, through various mechanisms like TC, for example, or MQPrio that I'm going to talk about later on. And then what happens is that the packet goes into the queue for your controller, when your controller at some point is going to send the packet. And when the packet has been sent, the controller will typically raise an interrupt saying, OK, I have sent that packet. You can now release any memory that was associated with it and free all of the resources. That's called the completion for a TX packet. So once you have the completion, so that is going to be notified by your controller, you can free the SKB. There are a couple more things that you can do. It's not mandatory, but it's heavily recommended. When you put a packet in the queue, you can indicate to the kernel how many bytes did you put in the queue. And when you release the packet, when you are in completion, you can say to the kernel, I have released these many bytes from the queue. And this will help the kernel to be a bit smarter when it comes to traffic pacing. I don't know if you ever heard about the buffer bloat problem, which is a typical problem dealing with traffic globally in the internet that will have a tendency to become high latency when you have a lot of data that is going through. And this is because all of the actors, the individual nodes in your link will have such queues and buffers all over the place. And so when you make the kernel aware of what is currently inside your queue, the kernel can, for example, start deciding to stop unqueuing traffic, even though you still have room in your queue, but just to keep that amount of queued traffic small to guarantee that you can have low latency traffic. So it's a good idea to add that in your drivers. On the receive side, it's a bit different. On the receive side, we have what's called NAPI. I don't know if you ever heard about NAPI. NAPI means NAPI. It used to mean new API when kernel 2.4 was out, so it's no longer new. And so the new API doesn't stand anymore. NAPI just means NAPI. And the idea is that you want to process packets without relying on interrupts to drive that. Because what typically happens is that you will have an interrupt that's going to be raised by your controller every time you receive a packet. So that's fine. But what's going to happen if you have a lot of traffic, and especially small packets, is that you're going to have your interrupt and then trigger the processing for your single packet, start processing it within the network stack, and then you're going to get interrupted by the next one. And the processing is going to start for that next one, and then you are again going to be interrupted, and so on. So this in itself will hurt the performances a bit. So the principle with NAPI is that when you receive one packet, the first one, you are going to start processing it, but keep the interrupts disabled. And instead of manually processing the packet, you are going to call within your interrupt controller NAPI schedule. And then the kernel will call into a function that you have registered. That's going to be your poll function. And it will say, OK, can you process the next 50 packets? That's called the budget, for example, while keeping the interrupts disabled. So you process it, and then you see if there is more things in the queue that you can process. So you process the next 50 packets. You don't want to do that forever. So at some point, when the budget is exhausted, you re-enable the interrupts, and you again start going into an interrupt-driven mode. And this will avoid all of these interferences. This is not batch processing. Batch processing would mean that you need to wait for n packets to be received before you start processing these. NAPI is not that kind of mechanism. If you want to do batch processing, you have to do it at the hardware level with a mechanism that's called interrupt coalescing, where it's actually your controller that's going to start keeping packets in the queue before notifying you that there is something to process. NAPI is just about avoiding all of these interferences from the interrupts. NAPI also works with TX. So in the polling loop that you will have, you can also process the completions for the transmitted packets. And what you can also do if you have multiple queues, especially multiple receive queues, is have one NAPI instance per queue, allowing you to have more control over that mechanism here. On the data paths, so transmit and receiving, you might also need to do something else that's going to be the timestamping. So It's useful for something called PTP. I don't know if you've ever heard of PTP before, the Precision Time Protocol. But timestamping can be used for other applications. What you want is get information of exactly when a packet left your controller. And you can only get that information from the hardware itself. Because from the software level, you know when you unqueue the packet, but you don't really know when it's actually going out. So in some cases, the hardware can tell you exactly when the packet went out. And the same thing for the ingress side. The receive side, the controller will actually timestamp the packet when it receives it before it puts it into the queue. And so it's going to be up to your driver to, while it's processing the incoming or outgoing traffic, to grab that information about the timestamp related to that event. So for the receive side, it's pretty simple. Okay, you grab your packet from your queue, either from the interrupt, the first NAPIPL or the subsequent ones. And then you also grab the information from your controller, what is the timestamp associated to that packet, and you put it in the shared information of your SKB. And it's easy, because when you receive the packet, you know that you also have the timestamp available. On the transmit side, it's different, because you are going to unqueue a packet, but it's not been sent yet, so you don't know what is the timestamp of the transmission of the packet. So you have to wait for the transmit completion, so for the driver to notify you, OK, I have transmitted that packet, in order to retrieve the timestamp. And what it means is that you need to keep a reference to the packet that you sent that were timestamped. So you need to keep a queue of SKBs that were sent and that needs timestamping. But it's a bit even more complicated than that. You need to check whether or not you need to timestamp a given packet. And that information comes from the kernel. So we'll have a flag that you check in your SKB that's going to be, do we need to timestamp it? And if so, I am timestamping it by stating the in progress bit in your SKB. And then, in any case, if you are or not responsible for timestamping it, it's a good idea to call the SKB takes timestamp, so that we can fall back to software timestamping if we cannot do it in hardware. And when you have the timestamp available, you can actually call that function having put the timestamp into the SKB. So what's happening here is that you are sending a packet, you keep a copy of it, you put a timestamp in it, and you send that copy of the packet that was sent back to the kernel, and it's going to go back to user space, and the user space will have the information of what is the timestamp associated to that data that I sent. You need to keep in mind that sometimes it's a bit more complex than that. Take a look at the documentation, because in some cases on your link, physical link, you can have multiple actors that can do the timestamping. For example, the Mac, but maybe the PHY will do the timestamping, and you need also hardware timestamping. Or maybe there is something else in the middle that can do the timestamping. So just checking at these flags is sometimes not enough. So in this documentation, it tells you how to gracefully handle that when you have multiple timestamping actors on the link. So that was about. I'm going to tell you about how do we configure that later on. So back to the queues, let's talk a bit more about receive and transmit queues. I said that it's pretty common right now on hardware to have multiple queues on the transmit and receive side. Why is it important? On the receive side first, it can be interesting to have multiple receive queues if you are, for example, dealing with an SoC that has multiple CPU cores. If you have multiple CPU cores, what you can do is actually associate each queue with a CPU core. And therefore, you can actually try to parallelize the processing of the ingress traffic. It's a bit more complex than it seems, because you don't just randomly assign an ingress packet to a queue. You need to actually keep some consistency with regard to what you are unqueuing. For example, we are talking about flows, traffic that have the same source destination IP, source destination port, will often be consumed by the same application. And therefore, it makes sense to unqueue all of that always into the same queue. You are guaranteeing the ordering in that case, and also the cache coherency. So the hardware itself needs to be a bit smart about how it's going to do the queue assignment. So you have two ways of doing that. You have what's called RSS, the receive side steering, where the controller will actually look at the headers of your packet, extract the important fields, like the IP address and the ports, compute a hash of that information, and take the lower bits of that hash to deduce the queue number. You are sure that all of the packets that have the same IP and ports will have the same hash, and therefore will go into the same queue. So you can configure your hardware to tell it how it should do the hashing. In some smarter hardware, you can actually steer the traffic. So actually say, traffic with this exact address and this exact port should go into that queue. And here you need some hardware that needs to be a bit more configurable in order to do that. So the user space APIs to configure that are going to be either iftool or the TC API. There are other things that can do some offloading of that, but it's the main entry points. If you are not familiar with that, first take a look at iftool and TC on how do you configure that. On the transmit side, it's a bit different, because on the transmit side, we are in control about what we are sending. So we know in advance where we should unqueue the traffic. There are, again, multiple use cases that we can have. One of them is what's called XPS, to assign, again, one queue per CPU core, to avoid here having contention on the queue locks. So you can unqueue traffic on multiple CPU cores at the same time. And so here, this is where we are going to actually use the SKB gate queue mapping. So it's pretty easy to implement in your controller, much easier than the receive part. On the transmit side, you just take a look at what's the queue mapping for your SKB, so because we know that in advance, and unqueue your packet in the right queue. You can do much more advanced things. For example, you can, if you have multiple queues, try to do some prioritization of the traffic, because the hardware usually have some kind of a scheduler in front of the queues to decide from which queue it should unqueue the next packet to be sent. And so sometimes it's configurable, and you can have like a high priority queue and lower priority queues, and everything that is in the high priority queue is going to be unqueued first, and then the other ones. And you can go even further than that to implement time-sensitive networking, where you can have queues that have such a high priority that you can do frame preemption. So basically, you are in the middle of sending a frame, you stop in the middle of that to send something else, and then you resume from where you left. So you need dedicated hardware support for that, but it's something that's doable, and all of that is configured through the queue configuration with MQPrio and TA-Prio, which I'm going to talk about a bit later on. Finally, on the hot path, the data plane, we have something called XDP. I don't know if you heard of XDP before. So XDP is the ability to run a BPF program, or an eBPF program rather, directly within your driver. The idea is that we want to run that BPF program to take a decision about what to do with the incoming packet as soon as possible. As soon as the packet arrives, we want to take that decision. And the sooner that we can do is actually, the soonest we can do is actually within your driver. So in your poll processing loop, when you receive a packet, you can run a BPF program, and that program will decide what to do with it. Modify it, drop it, forward it to the kernel stack, forward it to a dedicated socket with AFXDP, and so on. So this needs driver support. It's driver dependent. The first thing that you need is to use page pool for your buffer allocation. And then you need to implement two NDOs, the BPF NDO to load the BPF program in your driver. And then you need to modify your polling loop in order to run that BPF program when you receive the packet. And sometimes you can also have XDP at the TX level, at the transmit level, in order to take a decision just before you send the traffic, or to do some redirection between ports. The documentation here, there is a very good documentation and extensive by the Cilium project on XDP and BPF in general. And you can also take a look at some example drivers. For embedded systems, the one that we consider the reference driver is usually MVNeta, which is a driver for a Marvell platform. But it has support for all of the XDP features that are going to be interesting. So that was about sending and receiving data. Now, let's talk about how do we configure all of that. There are lots and lots of knobs that we can tweak in a typical driver because we have so many features that we can control. And the way that we are going to control that is a bit, well, not all over the place, but there are various types of APIs that we can use in order to do that. So we saw that we have lots of things we can do just when it comes to sending and receiving traffic. But another important bit would be reporting statistics about what your controller is doing. Like how many packets did you send and receive? Did you get errors? Did you get checksum computation errors? Can you get per queue statistics, at the MAC level or in the internal engines and so on? You can do a lot of offloading usually. So do you want to do the checksum computation in your controller or in software? Do you want to insert the VLAN tag for VLANs in the controller or in software? All of that is configurable depending on what your hardware supports. You can also configure, of course, the Ethernet-specific data, like what's the size of your MTU. Do you want to force the link speed at a given speed? If your controller is capable of going from 10 megabits per second to 10 gigabits per second, in some cases you want to force the controller running at 100 megabits per second, so you have dedicated control paths to do that. And an important thing is that some of the configuration operation needs to be serialized. So they are protected by a lock that's called the RTNL lock. And it's a very global lock that serializes all of the network configuration for all interfaces, avoiding some race conditions between multiple configuration paths that can run in parallel and sometimes do bad things. But it's not because it's the configuration path that it can go slow. Some hardware actually have bottlenecks on how long it takes to configure these, especially if you are doing a lot of offloading. You need to configure a lot of things in your classifier and so on in order to select the queue to unqueue the traffic on. Sometimes it takes a while to fill all of that data in all of your tables within your controller. So you might also need to think about how long it's going to take to do the actual configuration operation. Another example is that if you can avoid it, try to avoid bringing the link down when you do the configuration and then up again. Sometimes you have a choice, sometimes you don't. Sometimes it says in your hardware. If you want to change that specific setting, you need to first disable the link, change the setting, and re-enable it. If you can avoid that, it will make things much faster, of course. In terms of entry points within your driver, there are lots of them. We saw the NDOs, the net dev operations, like the backbone of the driver. There are other sets of callbacks that you can register into your net device. On top of the NetDev ops, you can have the ethtool ops. And as the name implies, these are configuration operations that are specific to Ethernet devices. They will really configure Ethernet-specific stuff. So you usually don't find that in a wireless driver, for example. But you can have a lot of these. I'm going to talk about the various type of ops that you can have. One thing to remember is that you should always configure all of these before you register your net device. So make it publicly visible to the user. There are other configuration mechanisms. One of them is the notifier mechanism. So a notifier is a way for your driver to indicate to the kernel, I am interested to know if there is any change of configuration in any of the network interfaces of the kernel, and I want to know about configuration changes into this and this and this data bits. For example, when you are adding a new VLAN interface that is bound to your driver, you want to know about that. Or if you are going to do some bridging with your interface within the bridge, you want to know about that. So these are hooks that you are going to register, and the kernel will call into that when there is a global configuration change. Even though if it's not on your interface, it can still be called. SwitchDev, for example, relies heavily on that. So it's for when you are writing a driver for an Ethernet interface that's going to be part of a switch on your hardware. So some hardware have internal switches with multiple ports that are going to be exposed directly outside of your SoC. And in order to offload the bridging, so the traffic forwarding between your local interfaces, you will have to use a SwitchDev interface for that. There is a kind of legacy ioctl interface for drivers. So ioctl is a mechanism to do some user space to kernel communication. And it used to be that your driver could implement specific ioctls. So basically, the user space would directly hook and send a message to your driver to do some driver-specific configuration. This is fading away. Most of the ioctls right now that are related to the networking are handled by the core or by dedicated frameworks, like the PHY framework. The last one that was handled by drivers a lot was the timestamping configuration to configure how your hardware should timestamp the outgoing or incoming packets, like all of these, or just the PTP packets, or none of the packets. So this used to be done through a ioctl hook in your driver, and now there is a new mechanism where they actually implemented NDOs for that instead of relying on ioctls. And finally, a driver like an Ethernet driver can also interact with other subsystems to do other things. A good example would be PTP clock. So for the timestamping, you have an internal clock that will run inside your Ethernet controller that will do the timestamping. How do you adjust that clock? Well, you will register your driver to another subsystem, that is the PTP clock subsystem, and you will have hooks and operations that are going to be specific to that subsystem, but are still going to be handled by your driver. It can also be the case for the MDIO bus. If your driver is also an MDIO driver, you will have to register a device for that. So for the NetDev ops, there are currently 92 defined NetDev ops. You are not expected to implement all of these. Usually a typical Ethernet driver implements between 10, 20, maybe 30 if you have a driver that does lots of things. The most important one I would say is, of course, the start XMIT to transmit data. The open and close operations, and they are actually mapping to when you do a link up or link down from user space. When you set the link up, so you enable the interface, the NDO open is going to be called. And when this returns, your driver should be capable of sending and receiving traffic. And same for the close. When the close returns, you should no longer be able to send and receive traffic. You have an NDO to gather statistics from your controller. You have an NDO to specify the receive mode. This one is also implemented in most drivers. This is to implement the infamous promiscuous mode. I don't know if you ever heard of that. This is when you want your driver to not do any kind of filtering of the incoming packet. For example, if you receive an Ethernet frame that don't have a matching destination address, one that doesn't match your local controller, usually the controller will drop the frame. It's not for me, I drop it. In promiscuous mode, you want still to receive that frame and send it to the user, usually to do some Wireshark or something like that to analyze the traffic. So you have to configure your controller to not drop these frames that are not interesting. As I said, there are 92 of these, and I'm only mentioning 4. For the rest, I encourage you to take a look at these. They can be used to configure the virtual functions, a bit of bridging, flow control over Ethernet, VLAN filtering, and so on and so forth. And as I said, some are really not related to Ethernet at all, because these NDOs are usually very generic, and they should apply to pretty much any net device. Another important bit of net device, and this is something that I struggled with quite a few times, is the notion of NetDev features. So this is actually an attribute that you're going to fill within your net device at any time to indicate to the kernel what is your device capable of in terms of offloading. So can it compute checksums at receive or transmit time? Can it do VLAN filtering? Can it insert or remove a VLAN tag automatically, or does it have to be done in software? Can it do RSS? Can it do flow steering, and so on and so forth? So all of these capabilities of your driver, you need to expose them to the kernel and to the user in the end. And this is what you see when you run iftool-k. It will tell you everything that is enabled or not in terms of offloading support for your controller. You have two main attributes that you will set within your controller. The features, so what is currently active on your driver at any time. So by default, it will do checksum verification and computation, for example. And you have the HW features. So HW doesn't mean hardware. It means, I think, human writable, host writable. It means the features you can change. If you take a look at iftool.k, it will tell you some features are changeable and some are fixed. So you are not able to change these. So the HW features is the one you can configure, actually. You can enable or disable at runtime. You need to specify these in your driver to see, OK, I can do that, and I can also do that or not do that. So I can do VLAN filtering or not. It is configurable. So you expose that to the kernel. And when the kernel wants to change the features, so either from a user request or for some other events in the kernel that will make these features broken, for example, the kernel will first call the fix features NDO in your driver for your driver to do some filtering of incompatible options, and then the set features to apply these. So I strongly encourage you to take a look at the NetDev features documentation. It's actually pretty good. You can feel that the person who wrote that faced the same problem as I was facing. Yeah, it will tell you more about the features management and how it can sometimes behave in a strange way. Let's now talk about iftool. It's actually an important part of an Ethernet driver. It's all of the operations that your driver can provide that are really Ethernet specific. It's not parameters, it's actually parameters, and they are accessible with the iftool utility in user space. And the way it communicates between user space and kernel used to be through ioctls, and now it's done through the Netlink API. And so you will, again, need to set a dedicated set of ops before you register your driver. All of these operations must run under the RTNL lock, so it's expected that you run these with the lock taken. And there are around 70 different iftool operations. If you want to see some information about that, take a look at this doc. So an example of what you can do with iftool, the information that you can report and configure. Statistics, lots of fine-grained statistics that your driver can expose that are not necessarily standard statistics, but really something that only your driver can provide. You can expose these with iftool. You can use the iftool hooks to configure the link parameters. For example, the user will tell you, OK, I want to actually set the interface at 100 megabits per second and have duplex and no auto-negotiation. All of these kind of parameters regarding the link are also configured via iftool. You can configure the classification. So when you receive traffic, on which queue does it go? You can use iftool for that, even though there are other interfaces. The RSS, so spreading the traffic between all of the queues based on a hash. This is also something you configure with iftool. So you will actually assign some weights on queues, for example. You will be able to do that. You can do channel configuration. So channel configuration is the mapping of queues to interrupts. And you have, well, lots and lots of other things you can do. You can configure the energy-efficient Ethernet. You can configure the interrupt coalescing if you want to do batch processing, wake on LAN, have information on SFP modules if you have some, and so on and so forth. You can even do some register dumps from iftool. So that's one of the main API for Ethernet devices. There exist also iftool operations dedicated to PHY devices, for example. Another path is going to be the TC. I don't know if you ever used TC before. It stands for traffic control. It's a tool that is pretty hard to learn. That's going to be used in order to do some traffic filtering, rate limiting. So I think shaping is rate limiting on the transmit side, and scheduling is rate limiting on the receive side, if I'm not mistaken, or policing maybe. You can drop some traffic automatically and so on. And the main idea is that you have lots of things you can configure, like, of course, queue mappings, but also a bit of firewalling, filtering, packet modification on the fly on both the transmit and receive side. And TC knows how to do that in software. But there are some things that you can offload to the hardware on powerful enough hardware. And so the main hook for that is, again, an NDO, the CTAP TC. And this is the only entry point for TC. And you have to look at the type field that is passed as a parameter in order to know which kind of TC operation you want to offload. Is it queue configuration, maybe to do some time-sensitive networking with TA Prio, or traffic shaping with CBS, Flower for classification, and so on. So if you want to look at the documentation, well, look at the code. There exists some documentation, but as a developer for drivers, the documentation isn't that great, and you would rather take a look at other reference hardware and other reference drivers to do that. Some other thing that is going to be pretty popular, well, that is pretty popular on SoCs for embedded devices is having embedded switches. So when you have your SoC that have multiple ports, and these ports can act as a switch. So you can actually do some forwarding between the ports, maybe some VLAN truck on VLAN tagging on the ports automatically. And you can sometimes offload that. So the hardware knows how to do that automatically. And the switch dev API is what you use in order to configure that offloading of the switching operations. And it's based on notifiers. So you register some hooks in the kernel to have information about is there a bridge? So are two parts of my switch bridged together? You get that information through notifiers. And when you, from your driver, you see that, you will configure actually the bridging to be offloaded. By default, when you write a driver for an Ethernet interface that's part of a switch, when you initialize it, the Ethernet interface should act as a standalone network interface. not as a part of a switch or whatever. You shouldn't do any bridging by default. It should act as a standalone interface. And then you should rely on all of the bridging support in the kernel to configure the offloading. Again, there are lots and lots of operations that you can do, adding into the forwarding database, the multicast database, the VLAN tagging, and so on. All of that can be offloaded in your driver thanks to the SwitchDev API. So if you want to take a look, again, at the doc, go see the SwitchDev doc. But this is a notifier-based API. It's a bit special. It's why I'm talking about that. Yeah, I'm going to try to go fast. Regarding PTP, I said that you can do some timestamping. In order to do some timestamping, you need an accurate clock. So there is a clock that runs within your Ethernet controller, and you might want to adjust that clock in order for that clock to be very precise, because the more precise and the more synchronized that clock is going to be with your system clock, the more accurate your timestamping will be. So you can provide through the PTP clock subsystem some callbacks in order to adjust the clock. You can adjust the frequency, or you can offset the time by a few nanoseconds or set the current time. And all of these are going to be used by the Linux PTP set of utilities within user space to synchronize the clock within your Ethernet controller that does the timestamping with the actual clock of your system, depending on whether your system has a trusted clock called the Grandmaster clock, or you want to actually consider the one that is in your Ethernet controller as your master clock and so on. So you can do some clock synchronization, and you need to specify callbacks to adjust it. You have lots of other things that you can do in drivers that I don't have time to talk about, but it behaves the same way as like install operations. You can do MACsec offloading, which is like IPsec but at the MAC level. You can do IPsec offloading. Well, you can do TLS offloading. You can do data center bridging for QoS. All of these have dedicated set of operations that you can register in your driver. Some final words regarding the PHY support. Because it's embedded here in Embedded Links conference, usually on embedded devices, you have a dedicated PHY that will do the actual modulation and transmission of the physical data. So the PHY driver is not handled by your Ethernet driver. They have dedicated drivers, but you need to interact with the PHY driver. When the user sets the link up, you need to notify the PHY that it needs to start discussing with the link partner to establish the link. And the same when the link stops, you should tell the PHY stop talking with the link partner and bring the PHY down to save some power. And then on the other hand, the PHY layer will notify the driver when there is something at the other end of the link. So the link becomes up because there is something else that was plugged on the other side. So there are two frameworks to interact with. PHYlib, which is the framework to write PHY drivers, and it exposes a few helpers that you can use within your driver in order to interact with the PHY, like start the PHY, stop the PHY, get the PHY description and definition from the device tree. It's not something that you should use nowadays in your driver. You don't really interact directly with the PHY subsystem right now. Instead, we use PHYlink, which is another level of abstraction. It uses PHYlink internally, but it gives you much more flexibility about the configuration of the link. Because sometimes some PHY might want the link to be reconfigured entirely. They don't use exactly the same protocol when you are doing 1 gigabit and 10 gigabits per second, for example. And so the PHYlink will notify your driver, OK, the link has changed configuration. Can you adjust your parameters locally? PHYlink also has the possibility for you to adjust the PCS. So now it's really down to the hardware level of how do you send an Ethernet frame. You need to encode it, and there is a dedicated block within your driver that does the encoding and decoding of the link, of the data, sorry. And so in some cases, you have dedicated IPs and dedicated drivers just for that part. And so you can interact with that through PHYlink. And in some other cases, the PCS is a component that is embedded within your Ethernet controller. But you can still write a driver in order to configure exactly that part of your controller. Some controllers even have several PCSs, and they will switch between the two depending on the link speed. And again, you can do that through the PHYlink interface. Some final words about how do you contribute to all of that. If you want to write some drivers for Ethernet controllers, you are going to have to deal with the networking community of the Linux kernel. And there are a few things that you need to know about. For example, in the networking community, we don't comment like any other community. We use a dedicated command style like this one. So you don't have to put the extra empty command line at the top. You don't have to write your comment in haikus. It's not mandatory. Regarding the variable definition, they use what's called the reverse Christmas tree, which is a fancy way to say when you are declaring your variables at the top of your function, you should order them from the longest line to the shortest line. It's just for the code to be pretty. Try to do that. Sometimes you don't have a choice. For example, if your definition depends on another one that is just above, it's OK if you break the reverse Christmas tree. But if someone comments on your code saying RCS, it's just, OK, I have just not aligned my definitions properly. If you want to contribute, you need to send your patches to the NetDev mailing list. The NetDev mailing list works with two Git trees, netnext for the new features, and net for the fixes. So if you have a fix to send in net, a new feature in netnext. You need to know that netnext closes during the merge window of the kernel. So when there is the merge window ongoing, you cannot send patches to the netnext mailing list in order to give the contributors a bit of break time, especially the reviewers. You need to know when you send a patch, which tree are you targeting, and you need to set that information in the subject of your patches. So there is the git command to do that. And keep in mind that the networking mailing list is very fast-paced, lots and lots of activities. The reviewers are doing their best to comment very fast, and usually you have a reply within 1 day or 2, and it can go even faster than that. So it's a very high volume. But if you can help with the review process, this won't hurt the community. It would be a good idea. If you want more information about the specifics of contributing to networking subsystem, there is this also documentation available. And it's now time for questions. If we have time, I don't know. And I hope you enjoyed. You are asleep already? It's the first day. Yes, there is one question.
How would you suggest starting to investigate packet errors or CRC errors?
OK, so the question is, how would I suggest to investigate errors like CRC errors or errors that occur within actually the controller? The first thing that we take a look at is the statistics. Usually there are counters within your controller that will tell you how many CRC errors there were. How many packets were dropped because of a malformed frame, and usually it's the first thing to look at. Then you can try running the same traffic, but with promiscuous mode enabled, so making sure that the controller doesn't drop anything, and then you take a look with something like Wireshark or TCPDump at what is actually the shape of your traffic, what does it look like, and usually Wireshark will tell you if you have CRC errors, and you can investigate that way. Another question? Well, thank you for attending, and I hope you will enjoy the conference.
Yeah, test, works perfect, good.
And then this one, same thing, if there's any questions.
Yes, I hope there will be. Is it time to start? No, we still have a few minutes. So anyone here knows device-free bindings? Anyone contribute patches to Linux kernel for DTS or bindings? Raise your hands. Maybe after the session, there's a coffee break. So maybe it's like get know each other, put a face. I'm reviewing a lot of patches, and I'm usually quite harsh, and I'm working on it. So putting a face to a review process will help me. So let's meet after for a coffee. We still have 1 minute. Okay, I think we can start going. So welcome everybody, welcome everyone. My name is Krzysztof Kozłowski. If you don't know how to pronounce my name, you can go by Krzysztof. I work in Inaro in Qualcomm Landing team. I'm also maintainer of device-free bindings with Rob and Connor. I take care about several other things as well in the kernel, Samsung Exynos, memory controller drivers, and a few other things. What I'm going to talk here today. So I will introduce shortly what is device-free source, what are device-free sources, device-free bindings. Maybe already you know it, then I will go fast through it. I will share why I'm working on the entire topic. I will describe the current progress, how we are with fixing of the validation errors coming from device-free schema. And I hope I will come with some conclusion whether the entire process is worth effort or it's not worth. So quick recap, the device-free itself is not tied to the Linux kernel. However, due to my interest and let's say my maintainership, I'm looking here from the point of view of the Linux kernel. The device tree itself describes the hardware, which is not non-discoverable for the platforms which need it in that way. So for the firmware or OS, when there's no other discoverable method, so no ACPI. The DTS are the sources. Then the DTC, which is the compiler, takes the source, creates the DTB, and how you have the blob. Now, how the bindings fit here. The bindings are the set of rules which describe how to write the DTS, and they also they document the interface. What's important here, they don't document the driver, they rather document the interface, how the driver should use it, and for different implementations. Now, the device-free schema is something relatively new in this entire setup. So this is a new format of the bindings. The previous one was a text format. And this new format has several benefits. First of all, it allows to validate the bindings against meta schema, so that the bindings are correct. And it allows to validate the DTS against the bindings. And this is what this talk is going to be about, mostly. Pictures worth thousands of words. So we have the device-free bindings, which impose a set of rules on device-free sources. Then the DTC compiler takes the DTS, creates the DTB. And now you have DT-schema package, which is a Python package. And this DT-schema takes the device-free blob, so DTB, takes the bindings, takes the meta schema, and tells you whether everything is OK or not OK. Now entire device-free sources and the bindings are in the Linux kernel repository in the main branch. DTS is used by several platforms, and not only ARM64, also MIPS, PowerPC, RISC-V. So at 6.8 kernel, we had around 3,000 DTS files. Each DTS file corresponds to certain hardware board, usually. Around 2,200 DTSI files, so the include files, which can correspond to some reusable component like a SoC, SOM, or some shared part. We also have overlays files, which I will not be covering here. We have around almost 4,000 bindings in the DT schema format. And to recap that, one binding file can cover multiple devices, so pretty often covers several different device types. And also SoC itself has so many devices that it's split to multiple binding files. We still have around 1,500 bindings in a text format, which will also impact the validation itself here. Now, I'm working on this. So I work mostly on the upstreaming of a new SoC SAM4 for Qualcomm. And if you have a mature platform and you upstream it, then you write quite a lot of DTS. And for example, the recent Qualcomm 8 Gen Snapdragon, the third one, had around 13,000 lines of driver changes and bindings, and 8,000 lines of changes in the DTS. So around 40% is the DTS if you upstream a new SoC. And this doesn't even include the PMICs, so the power management ICs, which are entirely reused from the previous generation. If you have incorrect DTS, you might have quite tricky bugs to fix, because these are closer to the hardware-related bugs. And now the DT schema is the entire here, the concept which can help you to find the bugs in DTS up to some level, and this is what the talk is also about. During my spare time, I'm still maintaining Samsung Exynos SoC, so this entire spare time, and therefore I'm kind of here, interested in optimizing my review time so that I want a tool which will help me reviewing and finding bugs, because no one pays for this, right? Now I'm working for Inaro, and I'm focusing on Qualcomm, and from the same reason, this is why I'm working on the Qualcomm on validating the DTS. Now, I started working on this, 5 years ago. So that time I was focusing on the Samsung Exynos platform. So the entire work starts with 5.3 kernel, and this number will be beginning of here several of things which I'm measuring. And since 2022, I joined Inaro, so I do the same for the Qualcomm, and this work for looking for validation warnings is around 5.18 kernel. So again, this number also will be quite important here. So what platforms here I measured and how I measured things. So first about the methodology. So I wanted to compare the validation of the DTS, of the device resources, against the bindings from several kernels, starting from 5.3. I actually measured much more, but there's no time to present all the data, so I chosen few kernels up to 6.8, which was last released. The warnings itself and the validation comes from the DTC, the compiler, and the DT schema. Now, the problem, of course, is the bindings and the schema change with the kernels. We can convert some text bindings to the DT schema, so this is why the most recent kernel has the most bindings converted to DT schema. If you go to the 5.3, there was a lot of bindings still in text. Bindings can also grow, deprecated, get improved, things like that, and the DT schema package also changes. So I remember that at some point I finished all the warnings for the Samsung Exynos, and then Rob Herring, another maintainer of device 3 bindings, he turned on some additional warnings in DT schema. So even though the DT bindings and DTS are supposed to be stable over time, they can a bit change. And the entire point of my methodology here that I was testing all DTS with the new kernel and with the new binding. So I was using kind of new tools to test all DTS. So also I used the newest DT schema 2024.2. Now, which platforms I was testing? DTS is used on several platforms like Arc, MIPS, PowerPC, but no one, I think, not many people work there to fix the warnings, so this is kind of not much work happening. RISC-V is using DTS, and the problem is that it's boring because everything is fixed. So I didn't include here RISC-V. So my interests are around ARM, ARM64, and because of limited time, I focus on certain just amount of platforms. So I tested several DevConfigs and collected warnings for these platforms. So for the ARM32-bit, I collected multi-V7 warnings. So this is the config which covers all of the most of the ARM V7 boards. Exynos and Qualcomm DevConfigs, which cover respective parts of the ARM32-bit Qualcomm or Exynos. For ARM64, I also tested the DevConfig, which covers almost all ARM V8, V9, ARM64-bit platforms. Exynos, which in that case covers a bit more, and this covers Exynos OC, Tesla, and Google Tensor. These are all Exynos. And of course, Qualcomm, which covers the Qualcomm guys. I mentioned before that we had around 2,900 DTS files, but I will not be testing all of them. I will not be collecting warnings from all of them. If you look at the DTB targets created by each of these DevConfigs, so for the ARM multi-V7, so this kind of things which covers all of the 32-bit ARM, not all, most of them. This is 1,300 boards, DTB targets. ARM64 DevConfig has around 1,000. So in total, we cover, with this test, 2,300 boards, which is not that bad. It's pretty nice coverage. And by the way, why I'm talking about DTB, because this is what the DTC compiler takes, and this is what the DT schema evaluates, and this is what actually maps towards the final board. So now a bit of history. Let's look how many of these boards we had. So the chart shows here number of the DTS makefile targets or DTB targets over time. The axis at the bottom is the Linux kernel version, so starting from 5.3. The big red stuff is ARM multi-v7, and it grown by plus 43% up to 1,300 boards. ARM64.config grew plus 300%, so from 250 to almost 1,000 boards from the oldest time. But a tremendous kind of change was here for the ARM Qualcomm. So ARM64 Qualcomm, 64-bit Qualcomm, started in 5.3 with 15 boards, and now it's 236. And this is partially the answer why I call this topic entire like a whacking a mole. So the point is that it grows so much that the moles are appearing faster than you can whack them. This chart will also appear a bit further because it also impacts whether we are able to actually solve the warnings. And about the warnings, I mentioned that there are two types of them, DT schema and the DTC. So DTC are the warnings which are produced from the device tree compiler, and they are there since all time, so what, 10, 15 years or more, right? So we fixed all of them, right? This is actually a boring topic, but the problem is that we didn't fix several of them for several boards. We still have many warnings, but if we didn't fix them, then it's actually done, boring. So I'll just show here a few results very, very fast. And this chart shows the total number of warnings per given dev config. So the big red spike is the ARM multi-v7. Which is absolutely huge, up to 5.18 kernel. I hid here some part. I will now show it again. So then at 6.2, it improved significantly. And this kind of almost zero there is ARM Exynos, which is nicely fixed, because for both ARM Exynos 32 and 64-bit, these are fixed. Only a few remainings are moved to the different config. Different warning level. However, I mentioned that this is the previous chart, that we have many, many targets, right? So the Qualcomm grew significantly, multi-v7 grew significantly, then ARM64 as well, right? So the total number of warnings doesn't tell you that much. It just, tells you that you have many, maybe makefile targets, especially because one warning can appear multiple times. If the warning is the result of error or something in the SOC DTSI file, so they include, it will appear multiple times. So the biggest platform, right, they will have the biggest amount of the warnings, and I don't want to punish active subsystems, so let's come with a bit different metric. So let's divide the number of warnings per number of targets in given kernel. And I'll be using this metric from now on to all further slides charts, so everything will be divided per number of targets. And if we look at the number of DTC warnings per target, it's getting a bit better. So still 32-bit ARM stands out, and all others are kind of nicely next to each other. And with 6.8 kernel, the Exynos is done, and the Qualcomm is kind of on par with the average. So yeah, still there is a lot of work to improve here, but apparently no one works on this, right? So just a reminder, Exynos is good. But I want to speak about something, yeah, I'm selling here myself. I want to speak about the DT schema validation, which is the new way of, let's say, looking at bugs in the device resources. So again, to recap, I'm testing DTS against the newest bindings every time, so all DTS, new bindings, and new DT schema. If the binding is not covered by the DT schema, so it's still in a text format, it will cause a warning. This is a warning by itself. And there is such, let's see this number of such undocumented or compatible is not in DT schema. So this is also divided per target. So ARM multi-v7 has a lot of things which are still not converted. And several others are significantly better. And for Exynos, I have, I think, one undocumented compatible in that way. Now, if we look at the warnings itself, and really the number, let's start with Exynos. So with 5.3, I had around 100 for ARM64-bit Exynos and 80 warnings per target for ARM32-bit Exynos. So this is a lot, right? It started getting better. So again, the bottom axis is the Linux kernel. The top axis, the horizontal axis is the vertical axis is the number of warnings per target. And around 5.18, I got really nice. And with 6.5, I'm done, so almost done. The only remaining one is because the binding is not converted to the text format. So it's possible to bring a platform to the 0 warning stage. Now, with the Qualcomm, it started the same, right? So it also started with around 120 warnings for ARM64 and 80 for ARM v7. Then things got weird, so it's kind of, some things improve, some things get worse. I would assume that much more hardware was added, and this is why there was that spike. But it's also the point which I would really worked a lot and hard to bring down the warnings, and we slightly succeeded. I mean, we drove it really nice to the, up to the 8 warnings per target for ARM64 Qualcomm. It's still not 0, so it's still not that good. If you want to see the chart and compare it with the average, so with the average, let's say, entire dev config for ARM v7 and ARM30, ARM9. So this is the combination of these two charts, and here the ARM multi v7 and ARM dev config are also added, so we can compare it with the average. Long time ago, everything had a big spikes. And this is the weird spike of the Qualcomm. With 6.2, we are getting better, and with 6.8, we are here. So the thing which are kind of the colors which we can focus on is the green, which is ARM64 dev config. So the average for ARM64 is worse than the Qualcomm, and the same kind of for the ARM32-bit Qualcomm. So ARM32 multi v7 has still a lot of warnings, but most of them are coming from compatibles not converted to DT schema. So my entire talk is whack-a-mole, right? This is the recap. These are the numbers from the previous one. So we started with 5.3 kernel, with around 80 warnings per each of these platforms, per target, Makefile target, and around 100 or 120 for ARM, Exynos, and Qualcomm. And here the average actually was better. So ARM64 dev config had much less warnings per target. With 6.8, we are partially there, but not really. So why whacking mole? This is the whacking mole is like a game where the moles pop up and you have to whack them. I don't know why people hate moles. These are amazing animals, right? So this chart shows number of targets and numbers of warnings. So the blue one is number of targets, which is for Qualcomm. It's only for Qualcomm. And the red one is number of warnings, total warnings. So we can see that both lines go somewhere. So number of targets, numbers of supported hardware grows slowly. Luckily, number of warnings gets down faster. And this simple production would tell that around 6.11, we would reach 0 warnings. I'm not sure if this is exactly true. More on that later. So why this is whacking moles? Some platforms are warning-free, so you can reach such warning-free stage, right? It's possible. But for some, it's very difficult. So there was a huge effort for the ARM Qualcomm to bring it down, and this effort still did not succeed. We are somewhere, but not there. And still is, of course, average per ARM64 Qualcomm, because if you look at the newest ARM64 Qualcomms, there are just few warnings for them. So the Snapdragon 8 Gen and the X Lite, they have only a few warnings. So we actually talk about here the legacy code, like old stuff. And the problem is that this old stuff is also growing and being improved, and we are not able to fix it down to 0. Now, is the effort worthwhile? So what does it give us? First of all, why are we fixing warnings? The trivial answer is that we fix them because the tool prints them. So this is why we have to fix them. But complicated, it's a bit more complicated, and I will try to evaluate them and figure out whether the warning is worth to fix. It's quite difficult to judge whether the warning itself is important or not. If you look only at the warning, so these are two examples of warnings, and they both say that some property for some node, so WR_ACT, does not match any of the regexes, or power supplies does not match any of the regexes. So this is the weird way how DT schema tells you that property is not allowed. And what does it tell you? I mean, basically nothing, right? You don't know the property should not be there. But does it mean that it's redundant, it's not needed? Or maybe it means that there should be different property. There was just a typo or some wrong name, and this different property is not required, but for this board, it should be there. Therefore, judging by wordings is quite tricky to say whether it's useful or not. Therefore, I would like to rather ask a person who investigated the wording and fixed the wording. So I would like to look at the commit message. And hopefully, all contributors write useful commit messages, right? So hopefully, everyone who contributes to Linux kernel say that why they are doing things. Obviously not. People say that this patch adds. So a little digression, if you ever contribute to Linux kernel, please always say why you are doing things, like you are fixing bugs of missing something in donkey drawer stuff, you are adding donkey drawer, or you are correcting the address of donkey drawer, or you fix a warning. And here goes the warning. From time to time, it's useful to say what you are doing if it's not obvious, but usually we don't know why you are doing things. So my kind of research here was about, I looked at all the commits which were touching DTS, tried to figure out whether they are the result of DT schema warnings, and then classify this kind of sort of work around the DT schema warnings. However, I looked only at the Samsung, Exynos, and Qualcomm platforms because of not enough of time. So if I look at the commits at Samsung Exynos, then from the time I was working on the Samsung Exynos to improve it, this would be like 370 commits for 32-bit Samsung and 144 64-bit. So if I have 500 commits to analyze. For Qualcomm, I was working a bit later, so only 5.18, so the last 10 kernels. And there we have 500 commits for ARM32-bit and 2,500 commits for ARM64, and to analyze and to figure out whether the commit is useful or not. I mean, that the warning is useful or not. So in total, we have 3,500 commits just for Exynos and Qualcomm. And this is also the answer why I'm not looking at other platforms like MediaTek or TI. Sorry, guys, I mean, not enough of time. Why I'm only looking at DTS? Mostly because the DT schema finds issues in your device resources. So mostly the DTS is the problem here. It's true that device tree schema could point an issue which is, after investigation, an issue in the binding and in the driver. But, and this is like a really issue which we have to fix in the driver. However, not enough of time. I mean, to find such commits, it will be much work, especially if people say what they are doing, not why they are doing. So mostly here is not enough of time. So of course, someone could say that I could put this 3,500 commits to ChatGPT, right, and just go buy NVIDIA stock. It's a great time to buy high, sell low. So instead I used more advanced technique called grep, and I was looking at the commit messages and trying to figure out whether the commit message is the result of DT schema validation. So I was looking for DTBs checks, certain keywords, also for fixes and CC stable, because this also points that something was fixing in the past. And this kind of identified me the candidates for the commits which are a result of DT schema. And then I look at these commits trying to figure out what they are doing, whether they're fixing real bug or they're fixing possible or just a style because whatever, right? So again, thanks to all contributors who said why they are doing things, not what they are doing. So I tried to classify first all the commits which are the result of DT schema. And this usually means that the committer knew that the DT schema points to this issue, right? So mostly you know that there's some warnings and you are fixing the warning, but not always. Sometimes of course, committer said that what the patch is doing, but sometimes the committer actually said that there is a kind of, he described the bigger picture, and probably I missed such commits. So here there's a quite big, let's say, error rate on my research. So in other words, I try to identify and find all the commits which were the result of DT schema and then classify them. Why I'm doing this again? Because if DT schema finds real issues, then DT schema is awesome. If DT schema finds just code style and looking things, then yeah. So the classification. I divided the commits or the issues to 5 groups. One is like a style issue, so something which is purely to make the DT schema happy. This could be like some node name change. Something which could be an improvement, so better hardware description. DTS describes the hardware, so we want to have better hardware description, maybe deprecated properties, use proper property, but still DTS is correct here. And then a possible fix, which means that probably Linux kernel works perfectly fine, but other user of DTS could be affected. There are other projects which use DTS, like U-Boot, and the DTS is actually not correct, even though there's no issue identified. Real fix, so something does not work or should not work, so this is really something which should be fixed. And I identified, by the way, a few things which were not pointed by DT schema, but they should be. We are not there yet, so a few things which would be a future fix. I understand this classification is subjective, and things, I based it on the commit messages and on the patch itself. So something which could be a style could be improvement, a possible fix could be improvement, or vice versa, and real issues could be a possible fix, or again, vice versa, right? So this is, quite subjective judgment based on my work. It's even trickier with the commits which are changing multiple things in one place. Actually, it was easier with Samsung Exynos because I was mostly only the one contributor there. It's significantly easier. I knew what I'm doing, but in the Qualcomm, it's a bit trickier. Several people were writing that they are doing something because of the bindings tell it, right? So yeah, this is quite, not sure why exactly, whether this is really things or not. So in the slides, I have a lot of examples of this classification and how I did classify it, but I'm not going to describe it here because we don't have time for it. So if you are interested, you can go back to the slides which I will post on the website. If you are interested in the future fix, so something which was not reported by DT schema, but will be, I hope it will be reported by DT schema. It looks like this. So basically, the p handle had an argument, and it should not have an argument. And this caused the Linux driver to fail to probe. This is very simple stuff, but this additional p handle confused the Linux driver, and the driver was actually not working. DT schema does not find it yet, but it might. You are nice on track, so let's go to the results. So to recap, again, number of DTS commits, a number of commits which were touching given platform, around 500 for ARM 32-bit, for Exynos, 32 and 64-bit, and 3,000 for Qualcomm, right? And commits which were result of DT schema validation, so the commits which are to fix a DT schema validation, which I figured out by my grepping, was around 40% for the 32-bit Exynos, 33% for ARM 64, and up to 22%, so up to 500, around 550 commits for ARM 64 Qualcomm were the result of DT schema validation out of 2,500. Now, what is the result of this classification of the commit per each group? So for ARM Exynos, we had 370 total commits, and 70 of them is, let's say, style. But I identified around 15 real fixes, and 15 possible fixes, and the 6 future fixes. And if I'm actually looking at 6.9 kernel, I would raise this number to 18 real fixes, because I found there one more thing to fix. The bars are very similar for ARM 64 Exynos. The ARM 32-bit Qualcomm is a bit different, but the most interesting for me is the ARM 64-bit Qualcomm. So here, around 60 issues were the real fixes. So something which was supposedly not working, really not working, or might really not work for other user which we are interested that, bindings and DTS should be portable. These are the total numbers, but I would like to rather look at the percentages. So here, the 100% are all of the commits which are result of DT schema validation. So for the Exynos 32-bit, it will be 150 commits, right? So 100% is not all DTS commits, but 100% are the DT schema validation result commits. So around 50% of the commits were style-related, and 10% were real fixes. This number would be a bit higher if you include this future fix to this one. Similar numbers are for the 64-bit Exynos. So again, 10% are real fixes. The 32-bit Qualcomm is a bit odd here, a lot of improvements, at least according to my eye. And for 64-bit Qualcomm, around 12% of things which DT schema points are the real issues. So let me drink. So to recap, around 50% of the things which DT schema points are kind of cosmetic style changes. And this is the effect how DT schema works, because DT schema is quite strict on certain patterns in your DTS. This, by the way, is quite helpful because it improves the quality of the DTS. Such DTS is usually easier to read, so easier to review, easier to maintain. If you want to fix all the DT schema warnings, you have to fix this 50% of the style-related issues, because this is the noise, and you want to reduce this noise to actually get to the proper warnings. 30% are around some sort of code improvements, some better DTS to better hardware representation in DTS, or for example, removing deprecated properties, which is also useful if you want to maintain your DTS. And around 10% are possible fixes, so something which could be for other projects, like U-Boot, other consumer of device resources. And 10% are the real issues or real bugs. So this is quite good, I think. I mean, I don't know what numbers did you expect. So you have a tool which in some automated way can improve your DTS. It can find you, to make it more readable, improve the code, and find 10% of real bugs in your code. So this is why it's nice to use DT schema. And the final also conclusion is that it's possible to get the platform to warning-free state. It's really nice to have, I mean, it's really doable. Just find a dedicated person, and you need to find the platform which grows very slow, because the Samsung Exynos is basically stalled, so there's not much development there happening, therefore it's easy. For the other platforms, especially like Qualcomm, which grows significantly, 1,500% more, right, over the last, 5 years. So for such platforms, it's quite tricky because the moles are popping up faster than you can squash them, but we might get there at 6.11 kernel or somewhere there. That's it from the slides. Thank you. So I will leave it here, and maybe you have some questions. Check if it's working.
Hi, thank you for the great talk. So does DT schema validation also work for YAML-based device tree files?
So the DT schema validation uses the YAML as the language to write. So the YAML is the main kind of point there, but it's only the language how you write the binding.
Okay, got it. Thank you.
Can you pass the microphone?
So 2 questions. The YAML files that are in documentation device tree, is that basically the schema, or is that separate from the kernel sources?
So the DT schema as a core tool which performs this is separate Python package. And this separate Python package contains something which is called meta schema, which describes how the entire bindings in the schema should be written, and the actual tool which performs the work. Now, in the kernel, you will have all the bindings. So all the bindings are then also, we call them that, written in DT schema format in YAML language. So we usually call it like the same word, like a synonym. But the actual tool is a Python package, DT schema.
I see, okay. So I'm wondering, like, to possibly prevent the whack-a-mole you describe, if this were to be moved in the kernel sources and maybe checkpatch.pl could automatically run it, for developers right away, so that, oh, my commit just introduced a new schema violation. Maybe I should do that. I don't know. What would be the overhead of that?
Yeah, that's an interesting idea. And we have certain bots on the mailing list which test and report. I think that the problem here that it's quite still a lot of noise around. So for example, if you add a new hardware for, let's say, some TI processor or Qualcomm processor, right? And you just add the board. So you reuse existing DTSI with the SoC. And this DTSI has some errors that they will pop up for your board as well, right? So you have quite a lot of noise, which is not your fault, because we didn't fix the existing platform. So this is why this probably could not be enabled by default. But for some platforms, it could work. So for now, you should do it kind of manually before you submit the patches.
Okay, thanks.
I think, sorry for that, there is the person waiting.
Yeah, thanks for the talk. So validation is always a great thing. Are there any efforts planned to do similar things for the compilation with symbol information? Like currently we have the problem that there are many boards where you have overlays, but they are not compiled with the symbol information, so technically you cannot apply these overlays. And then as a developer, first the board is added without this -add, and then later on it's by another guy, the add is added, but it's not very consistent. So is there any plans to improve that as well?
So if I understood correctly, the policy is that the overlay should be also the target. So overlay should be always applied to the base DTS, if the overlay, of course, is in the Linux kernel. Therefore, it should be tested as well. And you mentioned that several of existing overlays are not like this, and we kind of, I don't know, people convert them. But if you want to add a new overlay, this should be added in a way that it will be built and applied. So it will be therefore validated.
Okay, thanks.
I think you had a question.
Thank you. Should the schemas be updated only by the people who write the drivers? Asking because I've noticed some vendors have schemas that are too open-ended, and you see different types of styles basically passing through and still giving us, driver level errors. So they're not as diligent with the schema side as much as they are with the DTS side and the driver side. So should we go in and try to fix the schemas for them without knowing the long-term intention of their drivers or what their architecture is, or should we just leave it?
I would say yes. I mean, if you see that the binding, so for example, one way to improve situation is to convert existing bindings from a text to the DT schema format, so to the YAML, right? And this can be done by anyone. I mean, you don't have to know the hardware, of course. You can make some mistakes, but then someone else can fix it, right? It's open source. And in theory, also, the device tree bindings themselves and the DTS, they describe the hardware, not the driver. Therefore, I could just also imagine that the driver author will write the bindings for the driver, which is not what exactly we want. We want the bindings and DTS to represent the hardware. Therefore, you can decouple them. So the answer is that not only the driver author should write the bindings.
Okay, thank you.
Any more questions? Hands up. Okay, I will get there.
Sure. I was just going to comment on the whole check patch enabling type thing is, I've certainly run the DT schema testing stuff, and I always find myself a little hesitant before sending a patch to run it because it's such a pain, right? Like I know it's important, but I find myself sometimes sending a patch that touches device tree up and then relying on Rob's bot to tell me that I screwed up rather than doing it ahead of time. And I feel a little stupid for doing it, but it's because it's so heavy. And I wonder if the quality of patches posted and the number of things that slip through would reduce by quite a bit if it was a lighter thing, right? Like if somehow there was a tool that you could, even if it was slow, but you could just run it and say, how many new warnings were introduced by my patch? That's hard to answer right now. And it's a lot of work that everyone needs to figure out how to do themselves. And if that could be easier, that'd be awesome. So.
Yeah, I agree.
I mean, I guess maybe everyone knows it. I'm just like, I was just sort of bringing it up, and I'm not volunteering to do the work myself at this point. Yeah, I know, but it would certainly help.
So I guess entire kernel has the same problem of lack of automation tools, so that there's a lot of manual workflow. There are bots running, scanning mailing lists, telling you that they run something, but this should be done with simple command on your end, for example, or you push something to some Git forge, which does everything for you, right? But because it's distributed open source project, then no one is the owner, no one runs it, so yeah. Can you pass the mic? Maybe there further.
Oh yeah. If someone wants to get their hands dirty and start whacking some moles, do you have any advice where to get started with this?
Oh, sure. So one easy task is to convert existing text bindings to the device tree schema. And from this task, please always choose a binding, so the text, which has a in-kernel DTS. So because there are some bindings which have a driver, usually that's obvious, but they don't have a DTS inside the kernel. And such case is kind of less important. So the easy task would be to work on the text binding. And then, of course, while you convert it to the DT schema, you can run the validation on this DTS, and maybe it will point you to some issues. And second thing is probably you should avoid the most active platform. So for example, so I would be happy if you had Qualcomm, right? However, there's a lot of work happening in the Qualcomm, and if you are not into this process, then it might be a bit tricky for you. But there are many, many, many platforms which are kind of abandoned a bit, and you can just send warnings to, fixes for the warnings there, for the validation errors, and this will be welcomed, no problem. Of course, always there's a problem with the testing, so because you don't have the hardware. However, several issues pointed by the DT schema, as I mentioned, they have very little impact on the working. They are kind of style and improvements. So I did hundreds of patches which I didn't ever test except compilation and stuff, and they should be logically correct, right? So such work is an easy way to get into the kernel process contributing.
Thank you.
And hands here. Can you pass the mic so I'll be less jogging?
Yeah, thank you for your work on this. And one thing I want to add for the DT schema testing is, yeah, I was extremely annoyed by having it running by hand. So in the end, I started using GitHub and just wired the validation there after every push. And it works nicely. Just one thing which annoyed me a lot is showing the unconverted text files into YAML. So like you don't have the schema. So at least for ARM 32-bit devices, it helped a lot to just grab these out and just verify at least what has the YAML schemes. So I could like easily see if I have green or red pipeline depending on if something changed with new next kernel. So if anyone wants GitHub files, ping me for this.
Yeah, sounds good. I know that in the kernel there is already a CI file for a GitLab, so that for some projects it's possible to have, let's say, some GitLab pipeline. And maybe if we move it, add something like this too, because GitLab is a bit more preferred here because you could run your own instance. In the case of GitHub, you cannot. So if someone contributes something like this to the kernel, and then anyone could plug it to their own GitLab repo, then maybe this would solve for the active contributors. It will, of course, not solve all the drive-by people who need something done by someone else, but it's a nice idea.
It was really useful for merge request because like for Postmarket OS, where people trying to mainline new phones and tablets and stuff, they often are very newbies and they do a lot of mistakes. But this was very nicely catching like each new mistake they introduced the existing, like, let's say, still missing YAML files, but not having mistakes in existing validation.
Great, yeah, sounds good. And more hands up? Yeah, one there.
Yeah, thanks for the talk. You're just mentioning this for Linux, but does this schema validation also applies to U-boot? Because when I think of initiatives like ARM System Ready, it will be, in my opinion, it will be more important for U-boot because it passes the actual DTB to the Linux kernel. Is there support for U-boot on this?
So that's an awesome question. And I invite you to the talk by Sumit Garg, which is later, I don't remember which exact date, because there's an ongoing work to use the device tree bindings from the kernel and device resources from the kernel directly into the U-boot. So basically there will be, we export the bindings and DTS from the kernel at some point, like a new release, and take entire package as a whole to the U-boot. So then maybe you wouldn't need to run the validation on the U-boot side, because validation is done on the kernel, right? But if you reuse everything from the kernel, then you actually, you have the same errors or the same lack of errors. So I think that the solution to your case would be to switch to the in-kernel DTS and in-kernel bindings. And this is what Sumit's talk is about. So please find where.
So the ground truth of the DTS will be the kernel?
Yes.
Okay.
Yeah. So any ideas here to move the DTS and the device tree bindings out of the kernel are usually rejected for the main reason is that if you move it out, no one will ever review it. I mean, because, and this is even visible because the package DT schema is the Python package which is outside on GitHub repo, and it also contains some kind of core bindings for the core, let's say I2C, for SPI, things like that, right? They're also there. And the maintainers of the I2C don't look there because, I mean, they are not used to look there. They're used at the Linux kernel mailing list. So this is the big risk here is if we ever split it out of the kernel, the scope of the review of interested people will kind of significantly reduce. So probably the source of the knowledge will be always the kernel.
Tomorrow, 9:55 a.m.
Oh yeah, tomorrow 9:55 a.m. the Sumit's talk about using GTS from the kernel. Can you pass the mic?
Thanks. Is there any talk about getting Zephyr or FreeBSD to use the same DT?
No, I don't know.
Okay.
But this would be also a nice topic. I was always surprised to figure out that Zephyr went also with the YAML format, but entirely different and its own way. And okay, I guess that's it. Thank you for coming, and I will be there in the zone. So if someone wants to say hi, put face to a name, and shake hand, then I'll be happy. Thanks.
Hello?
All right, I think we'll get started. Hi, everyone. My name is Rajendra Nayak. I work for Qualcomm. I've been part of the Linux kernel team at Qualcomm for close to about 10 years now, primarily focusing on getting support for our various different SoCs upstream. The most recent one that I've been working on is the X Elite. So I'm here today to talk about our journey so far with respect to adding support for it in Linux kernel. So let's get started. Before I talk about the software and the Linux status, I want to spend some time on the hardware itself. This is our latest gen laptop SoC, which means that it's primarily targeted at a laptop form factor device. So you won't see this in, for instance, Android phones. This chip was announced in October of last year. There are no devices out there yet in the market, but we'll see a lot of these devices come out in the next 6 months or so in the second half of 24. This is not the first generation of laptop SoC from Qualcomm. We've had prior generations. I'll touch a little bit upon what's different here, what to expect in terms of performance, how does it stack up against competitors or the incumbents in the laptop space today. Then I'll talk about the work we've been doing over the last 6 months or so to get support for this merged in mainline. We're kind of halfway there. There's still a lot more things that we need to get merged in mainline. So I'll talk about what our next focus areas is over the next few months so that we make sure that this chip is well supported in upstream kernel. And then at the end of it, I wanted to show a quick demo with this device here that we have been largely using as our test platform. It's not a commercially available laptop. It's a test device at Qualcomm, which we call as a compute reference device. The support for this is already upstream. This is booted up with Debian with an almost mainline 6.9 RC kernel. Unfortunately, we couldn't get the external display working on this in time for me to kind of connect this to the projector and show a little demo out here at the end. But we do have a demo booth that our partners Lenaro have put up at the demo area. So this device is going to be available there for anybody to take a look in the demo booth. So like I said, this is not the first chip from Qualcomm which has gone into the laptop space. We've had these devices for a few years now. Some of them have had good Linux support in mainline. Some of these notable ones are the Lenovo devices. The C630, which came out back in 2019, I think, which was based on the Snapdragon 850, followed by the Flex 5G, which was based on HCX Gen 1, and then the last year's Snapdragon X13S, which was based on HCX Gen 3. So all of these had good Linux support thanks to the AR64 laptop project, which was a collaboration between Lenovo, ARM, Lenaro, and Qualcomm. So coming to 24, what's different? From a hardware point of view, the big difference is the CPU itself. There are other differences in other IPs, but the CPU is a custom CPU that's done by Qualcomm. This is the first generation of the custom CPU, which we call as Orion. And this is the first chip to have this chip in it, this CPU in it. So the X Elite comes with 12 identical Orion cores. These are split into 3 clusters of 4 CPUs each. They can go all the way up to 3.8 gigahertz. They support single and dual core boost of up to 4.3 gigahertz, which means that if you have just one CPU active in the cluster or one CPU in each of the clusters, 2 clusters active, it can go all the way up to 4.3 gigahertz. It's got quite a capable GPU, Adreno GPU, which can do up to 4.6 teraflops. NPU for AI use cases, which can do up to 45 TOPS. Standard LPDDR5X memory, all the way up to 64 GB, 16-bit 8-channel. Standard storage options for SD, NVMe, as well as UFS. This one out here has NVMe, SSD, or PCIe. Display primary interfaces supported are DP and EDP. And for video, we have a new video decode block which can do a whole bunch of encode-decode options, including the AV1 encode, which is new. And then we have standard camera ISP solution, standard Qualcomm audio solution, and then the cellular modem and the Wi-Fi is over external PCIe with an M.2 card. So I wanted to show a few performance benchmarks here for CPU, GPU, and so on to kind of give you an idea of how these compare against competitors, how this compares against our previous generations, and so on. But there have been at least a few queues of these which are clocked at different frequencies, devices which have different thermal envelopes. So there are a few different benchmarks available. So I didn't want to put something which is not completely accurate or is misleading, so I did not put any benchmark numbers, but you can always go and search for Snapdragon X Elite Geekbench, Geekbench benchmarks or some of the others like Cinebench, and you'll see a lot of data already, which is uploaded in the public domain. So instead, I just copied some of the, some of the press that's been around these devices of late, just to give you an idea of what to expect from these devices in terms of performance. So in short, these are quite capable. This is a quite capable SoC for a laptop space, both from a CPU, GPU, as well as from AI workload point of view. So moving on to software. So we've had this tradition at Qualcomm for a few years now that we post patches out for at least our flagship SoCs fairly early once the device is, once the chip gets announced, within a day or two. So you can see that the Snapdragon 8 Gen 1, Gen 2, Gen 3, all of these had patches posted out within a day or two of the chip being officially announced. We wanted to do the exact same thing for Snapdragon X Elite. So there was a lot of work that was done to get Linux booted up on these devices and patches ready for posting them for mainline post. The one big difference here is that the top 3 chips that you see are all targeted at Android phones. So we had active Linux programs inside of Qualcomm to get Linux up and running with Android, whereas the Snapdragon X Elite is primarily targeted at Windows laptop market space, but we still wanted to make sure that we have Linux support for these, and we are putting efforts to get it merged in mainline. In terms of boot firmware on these devices, it's standard UEFI boot. Linux boots up using device trees. It supports standard bootloaders like Grub and System dboot. This one here is booting Debian using Grub. DT selection is one of the open issues that we have at this point, which is basically how does the bootloader know which device is booting on when there are more than one device tree blobs packaged together in one software package, which is quite common for OEMs who come up with different kind of slightly different SKUs but want to flash one single software package onto these devices. We have a few ways of doing this in the Android world, and my colleague Elliot has a talk tomorrow, I think at 4:55, to talk about this specific problem and what we are proposing to kind of solve this in upstream. This is a very high-level boot flow diagram of how the device boots. So there's the primary bootloader booting out of ROM, which loads the secondary bootloader into internal memory, which then initializes the DDR and loads the Qualcomm Gunya hypervisor, and that runs in EL2. And then we have UEFI running in non-secure EL1, and then UEFI then loads Grub from the EFI system partition, and Grub then figures out where to find the kernel and and initramfs and all of this from the grub.cfg. In terms of kernel upstream status, we started off posting patches for these chips quite late into 6.7, so there was very little that got merged in 6.7, but we followed it up with 6.8, 6.9. So in the last couple of releases, there's been a decent amount of support that's already merged. We have pretty much all the infrastructure pieces around clock, spin control, power domains, interconnect, all of these merged. There's SMMU support, system cache. Both the reference devices that we use for our development, which is the CRD and another device, the QCP, both of these have support upstream. We have all the multimedia clocks merged, a bunch of file drivers, and the primary storage interface on these, which is NVMe or PCIe. We also have the DSPs being brought out of Reset, and the firmware loaded on these for some of the audio use cases. But this is, like I said, it's like we are halfway there in terms of having full Linux support for these. There's quite a lot of things that is missing, and that's primarily our focus going forward over the next few merge windows to get all of this support merged in mainline. So top of our list is primary display, which is over EDP, and then some of the power management things like getting the dynamic scaling working with CPU Frick and memory DCBS. DCBS stands for dynamic clock and voltage scaling. That's primarily the technique we use to scale the DDR as well as the caches. And then the low power modes through suspend resume, system-wide suspend resume, and then camera and video are the big missing pieces for now. A little bit more detailed into the status for display. There's been some rework that's been happening for the way the EDP and DP support today exists. The way it's been done today is to use two different compatible strings to distinguish between DP and EDP interfaces. But these are, at the end of the day, the same controller and the same PHY, so that was obviously not the right way to do it. So there's work happening to clean this thing up in upstream. So once some of this work gets merged, there should be DP and EDP support for X1 Elite merged as well. The main MDSS driver, which controls all of these panel interfaces, support for that is already merged. Support for that is already posted out. It's not merged yet. But once all of these patches that I've listed here get merged in mainline, we should have primary display working on interface working on these devices. For the external DP, though, we're still getting things working. It needs a retimer driver to be written and upstreamed, so that's still in the works. So we have it working with some monitors, but we're still trying to figure out how to make it work in all cases. In terms of GPU status, I think A740 is already merged. A750 patches are on the list. Neil has been pushing those to get them merged upstream. The GPU in this particular SoC is a slightly different variant of these. So there are incremental patches we have in our tree for now, which are not posted out yet, but we plan to get those posted and merged in upstream for the kernel as well as Mesa. And then the firmware is not there in Linux firmware yet, but that's also something that we're working on to get the necessary permissions to get the GPU firmware merged in Linux firmware. In terms of video, there's a new VPU block, video processing unit as we call it. It's a new generation of the IP as compared to the previous generation. The previous generation one was called Venus, this one's called Iris. So there was a new driver for Iris that was posted out in July of last year, but it was a completely new driver, not taking into account whatever that already existed. So it was obviously not the right way to do it, so there was effort done to kind of merge these two drivers together and have support for Iris added on top of the Venus driver. But then the way the Venus driver is structured, it was really hard to get these new functionality and new interfaces merged on the old driver. So for now, the plan is to write a completely new driver, but which also supports the older generation IP. So we'll have one driver, which is written from scratch, which supports Iris and Venus, and then over a period of time, deprecate the older driver for the older IP. It supports a bunch of these encode-decode options, including VP9 decode. Audio is fairly well supported upstream. The WCD codecs as well as the WSA sample speaker amplifiers were already upstream because they are reused from the previous generation. And then we had sound card and DMIC support already merged upstream. So speakers, the audio speakers on these devices, for instance, and the audio jack headset, everything works out of the box with the mainline kernel. There was also some things that had to be merged for the SoundWire interface because we had multiple speakers on one single SoundWire interface. We have two SoundWire controllers with 4 speakers on these. So those patches are, I think, pulled in as well. The only pending thing on audio at this point is support for analog mic. Camera, we have most of the infrastructure pieces already merged, clocks, regulators, and the PMIC support, everything that's needed to get the sensors powered up and so on. There's still work ongoing to get the CAMSS driver for this chip up and running, which is basically bringing up all these interfaces for CSI-Fi, CSID, and the VFE RDI interface. So once this is up, the plan is to get the same lip camera soft ISP solution working on these devices that we have working on the previous generations, which should enable us to do Google Hangout and Zoom calls kind of use cases with Pipewire-enabled Firefox. For anybody who wants to know more about the lip camera soft ISP solution, there's a talk tomorrow by Brian from Lenaro, who's going to talk about all the work he's been doing to enable this lip camera stack, soft ISP stack. In terms of power management, most of the active power management, which is the CPU scaling as well as the bus scaling pieces, are out on the list. So the scaling on this SoC is done in a coprocessor, which is the firmware supports the SEMI interface. So for CPU FRIC, we are using the standard SEMI-based CPU FRIC driver upstream. We also have a mailbox driver to communicate with the coprocessor, which is already posted out. There were certain things missing in the upstream SEMI CPU FRIC driver, like the boost frequency support and the limit notifier support for thermal notifiers that can come in to tell the kernel that certain frequencies are not available. All of that is either on the list or merged. For the bus scaling part, we have the same firmware supporting an SEMI vendor protocol, and we're trying to get the vendor protocol merged upstream. This is the first SEMI vendor protocol that's getting merged in upstream kernel, so it's taking a little while to sort things out and get it merged, but the patches are out on the list. And this should enable us to enable the scaling features for DDR as well as for our caches. In terms of low power modes, suspend to idle is already supported. We have support for CPU idle. While using suspend to idle to get into low power modes, which is system-wide low power mode, suspend, resume, we do have a few drivers which are misbehaving, which we are yet to fix, and then we are still not hitting the lowest power mode on these devices, which means that we need to go look at some of the votes which are not being released from some of these drivers so that we can hit the lowest power states. But that's something that we are actively working on. In terms of distro status, not much. We've been mostly playing around with Debian on these devices. So there's an experimental installer that's available openly, but it can only be used on these test devices for now. So in short, the roadmap for us for the next 6 months is to primarily get video decode fully functional in the kernel with an upstream driver. And not only that, but to get it working end-to-end with browsers like Firefox and Chrome, so that when you open YouTube and you're playing a video, if it's, for instance, a VP9 video that you're playing, it uses the underneath video decoder to decode the frames. Enable camera in the kernel, and also enable the libcamera soft ISP solution that's already working on previous generation devices. And this solution should be a lot more usable on these devices given the more powerful CPUs we have on these. We have a bunch of GPU, CPU optimizations in our internal tree, which we are yet to clean up, get it merged upstream. So these optimizations are currently not in a state where it's very generic to get things merged upstream, but we're working on getting them cleaned up and done in the right way so that we can get the best performance out of our GPUs and CPUs on these chip. And then power optimizations for the dynamic scaling as well as the system-wide suspend resume use cases. The goal is to get all firmware and Linux firmware as soon as possible. We're still working with the right people to get the clearances to get all these things merged in Linux firmware. And then finally, we are obviously open to working with OEMs when these devices launch and they come out, and with distro vendors who want to work with us and get some easy installers for people to get the distros working on, Linux distros working on these end devices when they are launched. In terms of the hardware that I have here, this is, like I said, the primary development platform that we've been using. It's called the Compute Reference Device. It's got the primary display on EDP. It's an AMOLED 14.5 inch. It's got a third-party touch support. It's got 3 USB Type-C ports, which all have DP alt mode support, so you can use them for external DP. Both WLAN and 5G modem on this are on external PCIe M.2 cards. And then it has a LPDDR5 16 GB of memory. These chips can support all the way up to 64 GB. It's got Spinor-based boot, and then the primary storage is NVMe over PCIe. And then there are 4 of these speaker amplifiers, the codecs, and DMics. In terms of the software setup that we have on these devices, it's running Debian 12 SID. And like I said, it's running an almost mainline 6.9 RC kernel. I wanted to give some more details on what almost mainline means. So we don't have a whole lot of patches on top of 6.9 RC to get this device to this current state. We have just 105 patches. Of these, about 78 are already on the list, which means they're posted. They are being discussed for getting them merged in mainline. And there are only 27 of them that we are yet to post out because, like I said, there are some of these are fixes, hacks that we are yet to clean up and get it in a state where we can post it upstream. So the link there is the link to the public tree that we've been using. All this code that's running on this is publicly available. This has GPU hardware rendering enabled as well as hardware video decode enabled, but this is using the video decode driver that's been out on the list. But that's not the driver that's going to get merged, so it's going to get revoked. So I think that's all I had. Yeah, so if there are any questions, I'll be happy to take the questions.
Just a quick question regarding like the Windows equivalent software. Like, where is that standing? Is it about the same, like, kind of half-baked, or is that further along? I was just curious.
You talking about the applications and some of those which are natively x86, and then are they ported over on ARM? Is that the question?
No, more like driver support. So like, for example, let's take the video pipeline or whatever, right? Or maybe your display port. Is that already working in Windows?
Oh, yeah.
Okay.
So all of that is working in Windows. The devices are going to get launched with Windows on them in the coming months. So Windows is like the primary OS, which is going to enable these devices. But we're working to make sure that Linux is well supported as well on all these chips which are targeted at Windows laptop market, so that anybody wanting to boot a Linux distro should be able to do that fairly easily if we have all the platform support merged in mainline, right? It'll still take some work. Like I said, we'll have to work with OEMs and with distro vendors so that folks don't have to do a whole lot of jumping through hoops to get this working, and there are easy to use installers and whatnot. But that's something that we are open to work with as these devices launch. So some OEMs are more open than some others, and so on and so forth. Yeah.
Thank you.
Yeah.
So I'm here I'm not on behalf of Seagate, but I work for Seagate. We're a hardware vendor. We sell hard drives. So I'm asking for some perspective because we don't have a whole lot of dedicated staff for patches to the kernel. We work on a lot of older stuff, SCSI mostly. So what's the distribution kind of work for these patches? Do you have a lot of full-time engineers on this, or is it, are you working with like Linaro or other companies? Can you talk a little bit about how that works?
Sure. So for now, it's not a very big team. You can say maybe max of 10 engineers across Qualcomm and Linaro, or maybe even less than that. That's the kind of folks that have been working on to get this to this level. But yeah, depending on the interest and like I said, as the devices get launched, if there are OEMs who are interested and so on, then maybe there's going to be a lot more people working. But at this point, it's not a whole lot of people. It's a very small team that's enabling this. Yeah.
That's more than we got, so that's so good.
Yeah.
Thank you.
Yeah. I think you can pass it on there, back over there.
Oh, sorry.
So I saw one slide where you mentioned you are using Debian with 6.9 RCs.
Yes.
And so for the end product, are you carrying some patches for boot time optimization, or like which bootloader you are using, or Falcon Boot or something?
No, so there is no end product at this point. So this is mostly us trying to use Debian as a way to, get the kernel things validated and merged in mainline kernel. So our primary focus is to get support for these SOCs in mainline, right? And then if there's an end product where we want to use Debian as OS, that's when some of these optimizations and boot optimizations and all those sort of things is going to come in. At this point, our primary focus is to try and get base support for these SOCs mainline, so that everything in the kernel space is in mainline kernel.org.
Thank you.
So, yeah.
So did you actually find something you thought would be easy turned out to be a lot harder than you thought doing this?
I didn't get that. Can you repeat?
When you were doing all this work, was there something you thought would be easy to do that ended up actually being a lot harder?
No, not really. I mean, we've done this before. We've done we've been, like I said, getting support merged for upstream for our flagship devices for a while now. So it was not the first time that we were working with upstream kernel community to get these things merged. There were obviously things we were doing for the first time on this particular chipset. For example, I spoke about the SCMI thing, the vendor protocol. That's the first time we're doing this on this chip. So some of these things which are first time for this SoC have been slightly more harder to get it merged upstream than, for instance, getting all the base support for clocks and regulators and whatnot, right? So there's already good support for those for our platforms upstream. So it was just a matter of adding this additional SoC support in those drivers. So only for the things which are fairly new and first time on this SoC, that's the only thing that's been taking slightly more time.
And one last question. So you said you produce your own ARM-compatible CPU core.
Yeah.
Did that provide any problems with upstream?
No, that was ARMv8 compliant, so there was absolutely no problem. It just, the kernel did not even need a single line of code change. It just booted up because it complies to the v8 spec. Yeah. Okay, I guess if there's no other question, we'll wrap it up. Thank you so much. Yeah.
Should work?
I would move your hand.
Yeah, sorry. Is this okay?
That's perfect. And then if there's questions and answers, you can use this microphone.
Yes.
Or you can repeat because it's being recorded. But there's an on-off switch right there.
Okay.
Thank you.
Thank you. think we can start. Hello, everyone. My name is Laura. I work at Collabora. And today we're going to be talking about testing the Linux kernel, and in particular, how we can provide better results to the upstream community. So we're going to start to talk about what drove us into looking into testing quality in the first place, why we think everyone should care about this. Then we're going to discuss the characteristics that we think make for a good test, especially when you run it as part of a CI. We're going to present some of our work, in particular the device probe K-self tests that we have developed and upstream recently. And we're going to discuss some other related work in the same testing quality domain as well. And finally, we're going to discuss what we plan on doing with all the tests that we are developing and what are the next steps. So first of all, a bit of background on why we started looking into this. So Collabora has been involved with automated tests for the Linux kernel for a while now, and we noticed that a large part of work in testing the changes that are sent by the developers over to the mailing list and part of the maintenance work from maintainers is still being done manually, or it's only partially automated. So we started to ask ourselves, how can we improve the CI to better support the maintainers to help relieve some of the day-to-day struggles for maintainers, and at the same time, how can we help developers test their patches beforehand and track any regression introduced? So there are already a lot of CI that are testing the kernel, but not every subsystem is currently being tested. So we think that we could leverage the CIs to better help the overall community. Of course, the kernel is a huge project, so making a comprehensive set of tests is a community effort. So we would really like to see the community more involved in this. And finally, how can we raise awareness on the importance of the CI and of running good quality tests? We started thinking about these questions, and we think that everything traces back to testing quality, in the sense that good quality tests will produce good quality results and reports, and this will be key to ultimately involve the community more. So as part of my work in Collabora, I've been working on kernel CI. Kernel CI is a continuous integration system for the Linux kernel. It runs a bunch of different tests on many branches and trees, and it reports any regression detected over to the mailing list. It also runs automated bisection, and Collabora has been helping both on the infrastructure side and also by adding new tests, monitoring the results. And we also have a lab with more than 200 devices that can be leveraged by kernel CI and other CIs as well. So in the process of adding new tests and monitoring the results, we started we started detecting some issues, and we also gathered some feedback from the email reports being sent by kernel CI. And yeah, we started to see some patterns and some pain points that we're going to discuss in the next slide. Currently, kernel CI is being reworked from the ground up with a new set of API and pipeline. So with the new system on the way, we took this chance to start analyzing the issues that we noticed and trying to come up with a plan to tackle them. So kernel CI is a community-led project, and it's supposed to be a tool for helping the community. So we would really like to see the community more and more involved in the project. But of course, a prerequisite for this is to first trust the kernel CI results. And the issues that we noticed over the years caused some kind of lack of trust in some of the results being reported. So we really wanted to restore trust in kernel CI first. So the main issue that we saw in the kernel CI legacy system were some unreliable results being sent over the mailing list. In particular, some reports being caused by false negatives that ultimately were not real kernel issues, but were caused by other issues such as infrastructure errors or errors with the tests themselves. So of course, to trust a CI, you need to trust the results and the reports that are being sent. And improving the testing, the quality of the tests themselves is going to improve the quality of the reports being sent. When you run tests on real hardware, false negatives is something that you have to live with, but we should at least try to minimize them or to provide enough data to the users so they can distinguish real errors from infrastructure errors or other types of errors easily. And from our experience, the large amount of false negatives being reported by kernel CI was caused either by poorly maintained tests or by tests that were using unstable ABI. One example of that is BootRR. It's a sanity checker. It's supposed to check whether devices on a certain platform are detected correctly by the system and that all the modules and the firmware related to it are loaded correctly. The issue that we notice BootRR has is that it relies on a static description of the hardware that needs to be provided by the users and maintained by the users over time. And also, in order to check whether a device was probed correctly to the driver, it relies on driver naming, which is subject to change. So if you run the same test on different kernel revisions, you might have inconsistent results. So this is one of the first things that we wanted to tackle. It's a pretty basic test, let's say, to check for basic functionality, and we wanted to replace it with something more stable. Another issue that we saw is fragmentation. That's not an issue per se, but let's say it's something to keep in mind. Everyone is running its own CI, which kind of makes sense because you may have different requirements based on the type of tests that you're running, on where you're running your tests. But we think that we should at least try to find a common ground for the basic tests. And it would be nice to have a set of basic functionality tests in tree so that everyone can use them in their own CI. So what are the characteristics for saying that a test is good quality? I think that this may vary, again, based on what type of tests and when you're running it. But there's a set of basic characteristics that we think a test should have, especially when integrated into a CI. So you want your test to cover for a good amount of functionality. You want your test to run fairly quickly so that you don't keep your lab devices occupied for too much time. You want your test to be able to run on different kernel revisions. And consistency is also a key factor, especially when you think of tests running in CI that do automated bisection. Flaky tests are kind of a nightmare when you're trying to run a bisection. And if you have inconsistent results, you may not be able to find the culprit commit easily. So we think that consistency should be a factor to keep in mind here. Maintainability is also another key factor. We really wanted to use stable ABI for new tests so that the tests, in a way, maintain themselves and at least there's not much user interaction needed over time. Output format compliance is also important when running a test in a CI. So for example, case of test as KTAP as a standard format. And if all of your tests are compliant with the output format established, then you can trust your CI to do a good job in parsing the results. And you can actually reuse the same scripts or the same parsers for multiple tests, which is always good. And finally, with our goal of wanting to get the community more involved in kernel CI, but in testing in general, we really wanted these tests to be adopted by the community. So we try to prioritize in-tree tests, case of tests in particular, over standalone out-of-tree tests. So with this in mind, we came up with a plan. We really wanted to focus more on quality than on quantity, so not just enabling a bunch of new tests or increase the coverage without paying too much attention to the results. So we try to enable the tests more gradually and really take our time in analyzing the results. And as I said, we wanted this test to be adopted by the community, so we try to prioritize in-tree tests, in general to reach a wider audience, but also to promote reusability of the same basic tests across different CIs. And finally, in the process of adding new tests, we wanted to make the kernel a little bit closer to testing, either by adding missing interfaces or reporting missing information to user space, for example. So we focused on case of tests, and we started working from there because we had a bunch of them already enabled in kernel CI, so we had already a wide set of data to look at. We could easily analyze the failures and the regressions being reported and see if there was any inconsistency. And we could also analyze the output format. As I said, KTAP is the preferred output format for case of tests. So with a wide range of results already available from us from kernel CI, we were able to analyze them and see which tests were missing, for example, output format compliance. And we also saw this as a chance to increase coverage in the sense that case of tests are already a well-established solution, well-known, well-documented. So we saw this as a chance to convert some of our unstable tests over to case of tests, which kind of fits most of the criteria that we consider for a good test. So we're going to dive a little bit more into the device probe case of tests, so the first test that we developed and upstreamed. And these examples will serve as just a guideline of what you need to keep in mind when developing new tests if you want to fit the criteria that we mentioned earlier. So as I said, the main pain point we had with the legacy kernel CI system were bootRR tests being inconsistent. And we wanted to come up with a solution to get rid of these bootRR checks, but also cover for the same functionality. So we wanted a solution that could use a stable ABI instead of just relying on the driver name. And we also wanted to get rid of the static description of the hardware as much as possible. So use some kind of dynamic detection of what's on the boards. And to cover for the same bootRR functionality, we came up with 3 tests, one for the DT device tree platforms, one for the API platforms, and one to cover for all the devices that were not covered by the first 2 tests. The reason why we split this is that we wanted, again, to get rid of the static description of the hardware. And on device tree, you have the device tree that works as a static description of the hardware. And for x86 and x86-64 platforms, you have ACPI tables providing pretty much the same information. So we wanted to leverage information already at hand as much as possible. And for all those devices that do not fit into this criteria, we came up with a 3rd test, which is supposed to be used only for the devices excluded by the first 2, and to cover for all those devices that are discovered entirely dynamically. So we cannot really expect to have a description of them in advance dynamically, but we need the user to provide it. So let's start from the device tree probe case of test. The goal of the test was to detect devices incorrectly probed among the ones defined in the device tree. The test relies on 2 lists. One list is a list of compatibles matching the device tree nodes to their driver. And this is actually generated by a script that's also upstream. The second list is an ignore list, which is generated by the user. And this is, like, let's say, the manual part of the test. And it's meant to contain compatibles for devices that are expected to match a driver, but not to be bound to it. At the moment, we only have 1 compatible in the list, and we don't expect the list to grow too much, so it should be fairly easy to maintain over time. The test then just iterates through all the device tree nodes. It checks the compatible string against the 2 lists, and finally verifies if the device is bound to a driver. And this is done by just checking if the driver folder is there in SysFS. So the entire test just leverages the information from SysFS. The test has been developed and upstreamed by my colleague, Nicolas Prado, and it's available since 6.6. You can actually try it out with the command there. And I left a link to the patch discussion if you're interested if you're interested in knowing what happened in the whole upstreaming process and how we get there. So for the ACPI platforms, we try to apply the same exact approach, but using the ACPI table information instead of using the device tree one. So again, the goal is to detect which devices were not probed correctly. And the test also relies on two lists, a list of ACPI IDs matching devices to drivers, and an ignore list to filter out just specific IDs, for example, for devices that do not require a driver but do have an ID. The first list is also generated by a script that's fully upstream. So again, we have only one little piece of information that needs to be provided by the user and maintained manually, let's say. The test just iterates to the ACPI objects in the ACPI tree. And for the devices that do have an ID, it compares it against the two lists. And finally, it verifies if the driver was bound or not by just checking the physical device linked, the physical node folder in SysFS for each ACPI object, and checks if the driver folder is there or not. So also this test only uses SysFS information, so information that is already available. However, the ACPI probe case tests, despite being based on the same approach as the DT one, had a bit more pitfalls compared to that, mainly due to how the information is represented in the ACPI tables and in the ACPI tree. So the ACPI tables have information both on platform devices, so devices entirely described by the platform firmware, and these have a hardware ID or a compatible ID that we can easily use to check which driver is supposed to be bound to it. And the ACPI tables also provide information on the discoverable devices. These have an address property, and they are discovered, of course, through natively through bus protocols. So we don't have any ID for these devices to be able to find the right driver. Also, not all the devices described in the ACPI tables may be actually physically there, because the same ACPI table might be deployed on different variants of the same platforms. So for this use case, we try to leverage the information from the ACPI glue layer, which is part of the ACPI implementation, and it's supposed to link the ACPI object to their physical object. So we just checked the physical node and firmware node folders in SysFS to be able to check for just the devices that are supposed to be physically there. And yeah, as I said, we did find quite a lot of pitfalls when looking at just the information in SysFS. As you may have some devices that do not require a driver, devices not assigned to any subsystem, so with no subsystem link. Devices that are linked to other devices, and these are the ones with a device link to another folder, and class devices. And all of these do not actually have a driver folder in SysFS, and that's expected. So we didn't want the test to report this as false negatives. So how do we handle that? For the devices that do have an ID, we can just put the ID in the ignore list. For all the other devices, so all the discoverable devices, we try to leverage the other information exposed by SysFS and try to do some heuristics in the test itself so that we can exclude some use cases. So this was submitted as an RFC. There's actually a second version. And it has been submitted a while ago, but there's no feedback on it. So if you want to try it out, and if you have better ideas on how to handle the exceptions, or in general, if you have any feedback, please feel free to stop by and leave a comment there. And finally, for the third test, as I said, we wanted a test to cover for the discoverable devices. In the ACPI case, the ones that were not described in the ACPI table. The goal of the test is, again, to detect which devices were not probed correctly. And this test relies actually on a per-platform binding. That's a manual YAML file that needs to be provided by the user that describes the hardware topology. So it lists all the discoverable devices on the system. And this is the part that is kept out of tree. The format has been discussed upstream and agreed upon, but the file itself is going to be kept out of tree. Well, the in-tree part is the test itself that just checks all the devices listed in the binding and just verifies if a driver folder is present in the sysfs directory or not. So unfortunately, we could not fit everything upstream, but we tried to find at least a compromise and fit half the test upstream and keep only a small file out of tree. This test has also been streamed by my colleague and is available from 6.8. And you can try it out as well. And there was an interesting discussion about this and how to upstream it at Plumbers last year. So there's a link to the discussion there if you want to know more, and a link to the discussion also in the mailing list. So what did we learn from this experience of developing these tests? We definitely gain a bonus pain point, which is that sometimes the kernel is hard to test. There's no standardized interface providing information, for example, on which devices were probed correctly. There was a bit of discussion in the first revision of the RFC for the ACPI case of tests. We would like to propose a solution and maybe come up with a sysfs tree or some kind of file in a format to be discussed to expose information in a better way, rather than having to do some detective work and having to parse the entire sysfs tree looking for information. We tried a couple approaches, having a file with a list of devices probed correctly or having a more structured tree, but we haven't yet found a solution that could actually simplify the tests in a significant way. But yeah, if you have any idea or feedback, please stop by in the RFC and let's discuss it. On the bright side, developing these tests helped us find and fix some regressions and failures. These are just a few examples of patches that we sent to fix issues found through these tests, but we actually found much more. So these tests already proved to be useful for us, so we hope they will be useful for the community as well. So besides the probe tests, we try to look at other things as well, such as fixing some of the case of tests already upstream. We noticed that a lot of them still don't use KTAP output, and we really wanted to fix this so that these tests could be integrated into kernel CI or CI in general more easily. And yeah, we did some digging through all the self-tests, and especially in the case of tests, and we already found some issues to be fixed. So we are trying to go through all the case of tests and fix output conformance and missing configs whenever needed. We also worked on some other areas besides device probe testing. We upstreamed the test for checking the properties in sysfs for power supply devices, and also a test to check if the Rust simple modules have been probed correctly. So we're trying to use the same approach that we described for the device tree tests to other areas as well. Right now, we're also looking at the part of the CPU FREC case of tests that do suspend resume testing. Would like to get this integrated into kernel CI as well. But I think there are still a couple of things to be fixed, such as KTAP output conformance. So we're looking at that at the moment. And we're also looking into making the kernel errors more reliable. That patch is just an example of it, of an issue that we try to fix. Basically, the kernel log is something that traditionally is only looked by human eyes. But if we can make the kernel errors reliable and consistent, then we can try and have them analyzed by a CI instead. But yeah, first we need to make sure that all the errors are being reported consistently and that the actual errors being reported are fatal errors, let's say, or at least they are reported at the right level. Unfortunately, we cannot fit every test upstream. There are certain tests that we worked on, and there's a couple of examples there that we cannot really fit upstream because they have a lot of dependencies, such as the decoder conformance tests that rely on Fluster and GStreamer. So there's a lot of dependencies, and you cannot really expect to fit everything upstream. And also, another example is a test that checks if the watchdog triggered the reset correctly. So whenever you have to physically reset the device and check if rebooted correctly, that's not something that you can easily fit in a case of test. But yeah, again, we're trying to develop it as much as possible upstream and keep out of G only the tests that have extra requirements. So what do we plan to do with all these tests? We are going to enable them in the new kernel CI system, and we really want to do this gradually. So we are trying from the basic to enable just the basic tests and checking all the results, fine-combing through them and making sure that the results are consistent and that we are providing enough data to the user. So as I mentioned, there's a new kernel CI system being worked on. You can check the blog post if you want to know, if you want to have the updates on the whole strategy. And we really want to involve the community more in all of this. And a community engagement working group has been created to help us spread the word and foster more participation from the community. This system, as I said, is being rebuilt from the ground up. So this is a good chance for us to really take our time with the results and make sure that all the tests work as expected. And in general, to shift the perspective a little bit and have more awareness on the long-term maintainability of the tests. So just to recap, we think that CI can really, really help developers and maintainers, and automated testing in general can help us. But the kernel being a huge project, we need help from the community and as many eyes as possible looking at this. So with this developer case of tests and the other related work, we started this effort, and that's just the first step. But we want to do much, much more in this. And with the community engagement working group being created, we hope that we'll get more involvement from the community. And yeah, that's pretty much it. If you want to know more about kernel testing in general, my colleague Pavel did a presentation earlier this morning. You can catch the recording, and that's all about the new kernel CI system. And my colleague Helen is actually going to have a talk later this afternoon about GitLab CI. So if you want to know more about pre-merge tests, you can catch the talk. And yeah, that's it. Oh, actually, I have one more note, which was added last minute, and it's about a meeting that is happening tonight at 7 p.m. at the Elysian Capitol Hill Brewery. And we can meet there. All the kernel CI folks are going to be there. And yeah, we can chat about what kind of tests you would like to see working in a CI, which kind of results you expect, and all about it. And if you have any questions. Let me just, I think it's working.
So I'm very intrigued by this notion of having an out-of-tree repository or database or something where people keep per board data files, or either lists of drivers to probe, or I can imagine that being useful for all kinds of things that would customize the tests for specific boards. Can you comment on the nature of that? Where is it going to be located? Who's going to maintain it?
So for the boards that we have in the Collabora Lava Lab, we're probably going to keep them in the kernel CI repository. So the description for the discoverable devices on, for example, Chromebooks and other boards that we have in our lab are probably going to be kept in the kernel CI repository itself, unless we find another common place. Like if this test is useful for other people, we can find another repository where to put everything. I agree that having a common place would be better. Maybe not even a CI particular specific repository will be better. So yeah, we can discuss this. The test is fairly new, so.
Yeah, I think just to complement a bit what she said, yeah, kernel CI likes position to have like those test specifications. I think we had the boot or, which is what we're replacing right now. But storing that kind of information as a kind of second level storage, some things you can have in mainline, other things like it's too complicated for mainline. Maybe you can have like all those standards and specifications and data inside like spaces for kernel CI.
Any other question? Oh, there's one over there.
So I guess I just entered when you mentioned about the watchdog test, because this is something that on the CIP side we are also dealing with, being able to test watchdogs as they expire with kernel CI. So you mentioned it's out of tree. Are you planning to upstream that? We are kind of working around it right now, as to my knowledge, but it's not really a nice solution. I think it's a pretty essential feature.
Yeah, what we saw is that there's the watchdog is self-test, but it just checks for the IOCTLs. So we wanted to actually check that the device has been rebooted. Yeah. But we don't think that this is ever going to fit upstream.
Why not?
Because how do you, the board is going to reboot, and we need a way to check that the device is rebooted using only the kernel interfaces available.
Yeah, I think, but I'm not totally into it, but I think my colleagues were doing right now is basically checking again that it's kind of, we're expecting now the reboot, and the next expected output of the kernel prompt at the end is going to be the login prompt. So this way we are kind of working around that this is now the time where the watchdog should kick in eventually. So it's kind of working, and in addition, we are not only testing the kernel watchdog, we're also testing a bootloader watchdog, because if you're observing AB updates, you want to ensure that the bootloader is also able to reboot your system when the kernel is stuck before the watchdog is running. So these kind of things are quite essential, and I think we should really push towards it. Now we are two organizations having the same requirement. I don't think it makes sense to say this is out of tree forever. We want to have the kernel CI system eventually testing that for us, and not we have to test it ourselves all the time. Yeah. That's what I mean.
For sure.
Good to know that.
LTP just did something related to this for tests that they create a new mechanism in LTP to deal with tests that need to detect when they've gone across a reboot. So it might be worth looking at what they're doing too.
Any other question? If not, I think we're done. I'm actually going to put a link in the presentation and re-upload the PDF with the details for the meeting this evening. Yeah, I'll update it right away. Thank you.
Can you guys hear me? Does that seem all right? Good. It's now 4:20, so it's the official starting time. It feels awfully like beer o'clock already to me, but perhaps we can, as a group, stick out one more presentation before we get our reward. So this talk will be about deferred work in the Linux kernel. I thank you for coming to attend at this late hour, and I thank the organizers for accepting this proposal. I'll say that all the demo code is at this GitHub repo. You should be able to download these demos and run them yourself, should you choose to do so. And the latest version of these slides, including any corrections I make due to errors people point out during the presentation, will be at this URL, which actually is HTTP rather than HTTPS. So with that, let's launch into the technical discussion. Deferred work is a common pattern in software engineering. It's not unique to the Linux kernel. It's inconvenient or inappropriate to perform some kind of callback function for one reason or another very often, and so the operating system queues it for performance later. For purposes of this talk, at least, there are two kinds of deferred work. I guess there's no pointer thing here. Oh, well. There's work that is waiting, that is delayed because a resource it needs, like memory, processor time, a lock, a message, is unavailable. And then there's work that is queued, that is performed in response to an event that occurs, classically a hard IRQ, but perhaps just a timer expiration or some device driver requesting work to be done later. So these is at a general level what deferred work is. Let's talk about what deferred work is in Linux. The two primary performers of deferred work in Linux for many years are soft IRQs, also known as bottom halves. In the soft IRQ code in the kernel, you very often see _BH_, and that stands for bottom half, which is what Unix called its equivalents of soft IRQs before Linux even existed. And then the other long-standing performer of deferred work, which is actually quite different than soft IRQs, are work queues whose executors are called K-workers. And why might you get interested in these topics if you, like me, are the maintainer and caretaker of a Linux kernel and a robotics project? And the answer is these kernel components find you in the form of bug tickets. There are two major ways in which deferred work can go wrong. One is that while work can be deferred for a while, it can't be deferred forever. A notable case of work being deferred for too long is RCU stalls. RCU is read copy update. It is basically the kernel's garbage collector for memory that is no longer in use. Obviously, garbage collection doesn't have to run right after memory could be freed, but if it never runs, then what you have is another symptom of work being delayed too long is that when there is a storm of network packets coming into the device, your user space application just completely falls over. In contrast to tasks being deferred for too long, you can have the situation that your performers of deferred work get on the CPU and just run and run and run and run, and they don't let user space make progress. So you can see K-workers or the executor of SoftIRQ's KSoftIRQD just sit on the cores, or ironically, you can see a K-worker watchdog fire because a particular work queue isn't yielding the processor. And I'm going to show some examples of these problems in the upcoming slides. So the difficulty with these situations is they've been traditionally hard to investigate, and they've been hard to fix even when you develop theories as to what's going wrong. In fact, SoftIRQs and work queues have the reputation for being a little bit inscrutable and hard to understand, and this reputation has been largely well-deserved, I would have to say, in general. But the point of this presentation is essentially to open this window and to give you some tools to investigate these kernel functions and to some extent do something about them. So with that, let's talk about SoftIRQs. SoftIRQs have been in the kernel apparently since the 2.3 series. I gave an earlier version of this talk, and somebody asked me what is the best documentation for SoftIRQs. And actually, I found it's Robert Love's 2010 book called Linux Kernel Development, while the actual callback functions that perform the work of SoftIRQs have changed during this time period. The core API for SoftIRQs is really about the same as it was in 2010, and Robert Love is a great writer, so I recommend that book. On the other hand, work queues, as I will describe, have changed a great deal, and so for the most part, the discussion of work queues in that book is kind of gathered some dust. But anyhow, let's launch into SoftIRQs. Let's start off by talking about what they are. There are 10 delicious flavors of SoftIRQs. They're listed here in the order that they appear in the kernel. So when KSoftIRQD runs and it comes along and starts executing SoftIRQs, it does first the high priority ones, then some timers, then some network callbacks, block devices, IRQ poll, which is essentially NOPI, if you know what that is, for storage devices. The most numerous SoftIRQs are actually tasklets, which are used by a lot of device drivers. There are scheduler SoftIRQs, HR timer SoftIRQs, and RCU SoftIRQs, as I already mentioned. Without studying SoftIRQs a great deal, you may notice that network receipt SoftIRQs are higher priority than HR timer SoftIRQs, and that already is kind of a hint that there could be problems. We could reorder these if we wanted, but that would be an ABI break, and potentially be unpleasant, say, to out-of-tree device drivers for those who care about things like that. So it sounds like a great design in general to have a callback associated with a hard IRQ that performs the lengthier work associated with that event. But in fact, I would have to say that soft IRQs are not the kernel's most beloved feature. Here are some money quotes from famous Linux kernel maintainers about soft IRQs. This one, soft IRQs are often a pain to deal with, appears in the kernel's official documentation. So it's not just my opinion, it's actually a fact. Here is a quote from Friedrich Weisbecker, who is a Linux kernel fellow, who said people fight hard through this big soft IRQ lock. Here, Friedrich is making a reference to the big kernel lock, which took years and years to remove from the kernel. Why are soft IRQs like the big kernel lock? The answer is that it's a well-established principle in software engineering that a lock taking and a lock release should immediately surround the data that the lock is protecting. You want to hold the lock for the minimum time possible. We are not following this principle with soft IRQs. There's a function called local bottom half disable that I'll talk more about in a moment, and it is scattered all over the kernel. And people do not know really what data it's protecting, and this makes it very hard to change. And then finally, the dean of real-time Linux, Thomas Gleichner, has said that soft IRQ processing prevents the kernel to control it, and the heuristics people have added are disgusting. So if you can steel yourself, I'm going to show you now the disgusting heuristics, which are in a file called kernel softirq.c. And the heuristics are these two. One describes the time slice that the soft IRQ processing will use in any one go. And then the second one describes the number of times that the kernel will go through that list of 10 soft IRQs before it yields the processor. So you probably know about Linux, that it runs on teeny IoT devices, and it runs on supercomputers. And so you might ask, why are these numbers, which are compiled into the kernel and not dynamically set by the scheduler, ideal for both supercomputers and, say, lawn sprinklers? And the answer is, it's hard to believe that they are. So we have the incredibly sophisticated schedulers. We have this new EEVDF scheduler. We are taking the power of those algorithms away and compiling these numbers in, but people just are frankly too afraid to change them. So let's talk a little bit more about how soft IRQs work or don't work. This diagram is intended to describe the actual mechanism. We have a hard IRQ. The soft IRQ management code checks if a soft IRQ is already running on that core. So ksoftirqd, which executes soft IRQs, is a kernel per CPU thread. This local bottom half disable big soft IRQ lock is protecting data that's local to each core. If the hard IRQ interrupts a soft IRQ, then a new soft IRQ cannot start. So the ideal situation is when the hard IRQ happens, if no soft IRQ is running, then you go immediately to this do soft IRQ function that executes soft IRQ. This path is called the piggyback. It's great when it happens. In voluntary preemption kernels, the hard IRQ is running in interrupt context, and the soft IRQ runs an interrupt context, and all is great, and then whatever was running before resumes. The problem is if a soft IRQ was interrupted by the hard IRQ, then you have to wait for ksoft IRQD to run. Ksoft IRQD does not run an interrupt context. It is a kernel thread which is managed by the scheduler. It's great that the scheduler is managing this thread, but it rolls up all 10 of those soft IRQs, and it's just this kind of black box. The situation is even more painful in real-time kernels because, of course, in real-time kernels, the hard IRQ is itself a thread. It is running in process context, and it doesn't make any sense for the soft IRQ to run immediately after it. It's just another thread. So the delay here can be for a while because ksoft IRQD traditionally runs in sched other with low priority. So in RT in particular, the situation is painful, and there are ongoing efforts to improve it, which I will describe in a moment. But first, I wanted to look at the question, how can we tell what ksoft IRQD is actually doing? So here I have, I just have some scripts in this GitHub repo that can give some information about that. The best method I've found to really investigate ksoft IRQD is just the stack count Python script that comes with libbpf. Here I'm going to use it to trace the function do soft IRQ, which this is a live demo, so here are some live warnings. What's happening now is liblvm is compiling some BPF. It's submitting it to the validator inside the kernel, and the virtual machine inside the kernel is actually executing it and outputting this data. So what stack count outputs is counts here at the bottom of different stacks that end in the execution of this function do soft IRQ. So you can see how do soft IRQ and soft IRQs are occurring on the system. So here we see an example of the piggyback. There's an IRQ. When it finishes, it enables soft IRQs and do soft IRQ runs. And if we scroll through this, here we see ksoft IRQD was running a soft IRQ, and even in this case, you can't really tell what ksoft IRQD is doing because the scheduler is just running it. So just for fun, I've made a BPF trace script that spies on soft IRQs and is just outputting on which core which soft IRQ is running. And here you can see sometimes they take a long time, and this is where the source of this difficulty comes from. So while I had fun making my own scripts, the real class way to investigate soft IRQs going forward that I would recommend you learn about tomorrow in the room next door is the tool RTLA that Daniel Bristow de Oliveira has created. This is a fairly new tool. RTLA, is kind of misleading in that you might think RT is real time, but actually it's the runtime latency analyzer. It will work with voluntary preemption kernels. It combines the best features of ftrace and cyclic test, which may sound like faint praise, but actually I mean that as a compliment in this particular case. It is a very lightweight tool because it is using trace points, and so you could run it all the time, I think, in production as kind of a black box data recorder and dump out data that shows what soft IRQs, for example, are doing when you're having a problem with your user space applications. So this tool is really nice, but I'm not going to demonstrate it or talk more about it because Daniel, who wrote it, will be speaking tomorrow. So with that, I would like to talk a little bit about the various ways that you can adjust soft IRQs and what prospects there are for future progress. There is a kernel configuration parameter called RCU new callback CPU. And what that actually is a parameter that will take soft IRQ processing and put it in its own kernel thread. And that means that you could pin this thread on your housekeeping cores of your robotic system. You can adjust its priority. You can adjust its scheduler variety. This option has been around for a long time. Similarly, since the 5.12 kernel, you can take the NetRx soft IRQs out of KSoftIRQD and run them in their own thread and also configure them. Similarly, this sounds really great to have this additional amount of control, but it's worth pointing out that both RCU and the network stack have an insanely large number of tunable parameters available via sysfs or via kconfig. In addition, there's even some parameters in procfs that directly control the behavior of network soft IRQs. So making your own kernel threads is a little bit of a brute force solution. Anytime you have a new kernel thread, you have a context switch penalty associated with executing it. So if there's anything I've learned managing these systems is that you have to perform measurements and see which configuration changes actually make your system work better. It's very tempting to put everything in its own thread because it's a simple solution, but it may make the system slower. A long-running saga is that of timer soft IRQs. Assuredly, if there's any callback to an interrupt that you would like to run quickly, it is the callback to a timer. And there have been a couple of attempts in the real-time kernel to pull timer soft IRQs out into their own thread. They've been not entirely successful, I would say, as far as how well they perform. There are two more recent attempts to make timers run in their own kernel threads in the voluntary preemption kernel, which obviously also could be used in RT. One proposed in kernel 6.5 was from Frederick Weisbecker, where he started trying to mark individual timers as able to run concurrently with other soft IRQs. That unfortunately ran into locked up problems and didn't get very far. The attempt to get rid of bottom half disable one instance at a time that seems more promising is some attempts to replace it with local scoped locks in the network stack. So this is an effort from Sebastian Sevier, who's right here. He gave a really great Linux plumbers talk about it in 2023. All these blue texts are hyperlinks, so you can go and look at it yourself. You may not know that the kernel now has scoped locks, so you can essentially put a mutex in a driver, and you don't have to have any go-tos that release it, because when the lock goes out of scope, the kernel will release it automatically. So this is great. And the idea is to replace eventually some of the calls in the network stack to local bottom half disable with actual locks surrounding the data that they're protecting, which would just be a giant step forward. Finally, I'll just mention, so this local scope locks unfortunately did not make it into 6.5 either, but I hear from Sebastian that this effort is ongoing and maybe there's hope that it could be merged. And I should say the demo he showed at Plumbers shows that when you use this mechanism, priority inheritance actually works with soft IRQs. That would be great. I would stop thinking and talking about soft IRQs if that would happen. That would really make me happy. Been thinking about them for a long time. But, oops, I just mentioned a headline feature in some sense of the 6.9 kernel at the end of the merge window was that the tasklets are now using the work queue API, tasklet soft IRQs, but it doesn't make sense to talk about that until after I talk about work queues, which I'm going to do momentarily. I'll just say to summarize this whole section that there are about 250 call sites for the big soft IRQ lock, local bottom half disable. So it is quite a long-term, difficult project to get rid of all of them. It's possible, as I mentioned, to run RCU and network callbacks, and in RT at the moment, timers and their own threads, but doing so has a context switch penalty, so you might want to consider other methods of adjusting them. And let's move on to work queues and talk about the changes to tasklets. So does anybody have a burning question before I dive into work queues? I'll take that as a no. They'll have successfully put the audience to sleep. But let's now talk about work queues. Work queues function quite differently from soft IRQs, mostly in happy, good ways. What a work queue really is just a linked list of function pointers that describe work to be done. A device driver, a file system, a crypto engine can enqueue these work functions. Each one of the work queues belongs to one of these kernel entities, but two different work queues can be associated with the same worker pool, which contains kernel threads that will execute this work. And here I am discussing bound per CPU work queues. So each CPU has a niceness 0 worker pool created by the kernel at boot and a high priority nice -20 worker pool. And work queues are matched to the pools depending on their flags automatically. And a given pool can contain, a given queue can contain multiple different work functions. You see this, for example, in memory management, that a whole bunch of different memory management functions can be on the same work queue. So these are the bound per CPU work queues. There also are unbound work queues. If we look at, let's actually just go and look at the process table on this system. So here are the K-workers that are actually running on this system right now. And if we look at, here's a typical K-worker. The number after the slash here is actually the core on which it's running. The number after the colon is just a counter, an ID. It's actually not of any interest. Yeah, so let's see, let's do this. So these ones with the U after the slash, these are the unbound K-workers. So they can run on any core. You can see that the numbering of these unbound K-workers has gaps. So for pool 16, we have 1, 2, and 4. There used to be a 3, and it went away. That's because unbound K-workers, which perform persistent CPU-intensive work that basically has to go on all the time, pretty much. They are, so both bound and unbound K-workers don't have a fixed number of workers per pool. The kernel provides them or tears them down as needed. Unbound K-workers also have a variable dynamic number of pools. Bound K-workers obviously can't migrate. They are kernel per CPU threads. Unbound ones can. That is great from the point of view of getting this long-running intensive work done. But I put it in red because it also means that if you have some task like logging, say, that is going on forever at some low rate, that isn't at all latency sensitive, running on your housekeeping core, because the unbound work queues that service the file system and the block devices can migrate, they can migrate to the cores where your latency-sensitive user space applications are running, which may be surprising and unhappy to you. So here's an example of how I got interested in work queues. This is an actual splat from dmesg, where the K-worker watchdog reported that a single work queue was persisting on the core for 207 seconds, which is a long time for a K-thread. This is an example, I should say, from the 515 RT kernel. The dmesg output reported that there were 3 active work queues on that core, one for the network driver, one for ext4 file system, and one for a device driver whose name has been redacted. These 3 work queues were assigned to this pool work queue 112 because they all have the byte A as in their flags, which means they all had the same characteristics which caused them to be assigned together. Now, if you have experience working in this area, fixing these kind of kernel bugs, you might say, well, I'll pin some thread on the housekeeping cores, and I'll adjust its priority, and I'll change its scheduler parameters with task set or CHRT. This is kind of the usual workflow for, say, kswapd. You can put it on core 0 and have it not be where your latency-sensitive applications are. However, that actually will not work for work queues. And this is the main message I'm trying to leave you with in this part of the talk. Work queues are great. Work queues are more controllable than software queues. Yes?
There is a mask for work queues?
Yes, that is what I'm going to talk about. But yes, so there's a way to work with work queues, but it's not the way that you're used to. And the reason is, if you look at the proc PID files, there's a file called stat. In this, stat file, there is this bit mask, which is actually an export of the flags from struct task. And I created this little program that reads each file in proc PID stat and checks that bit to see if we can pin that, that K-worker. Whoops. And in fact, you find that every single K-worker is unpinnable according to that bit. And you might say, you just said that all these unbound work queues can migrate. Why would they be unpinnable? That doesn't make any sense, right? If they migrate by themselves, why can't you migrate them? And so the answer is, you're doing it the wrong way. So in the work queue API, you do not manage the K-workers. You manage the work queues. The result you end up with is that the work queues, which are these linked lists of function pointers describing the work you want done, have a CPU mask, a niceness, and a migration affinity scope associated with them, which seems really weird. But if you think about it, who cares about kernel threads? Why do we have to think about kernel threads? What you want is this work to get done. You don't care which kernel thread executes it. So the great thing about work queues is that you do not manage the threads. You express to the work queue API what you want done, and it provides kernel threads that do the work that way. So this is actually really great, but it's somewhat profoundly different and bewildering if you start thinking about work queues and you've previously, for example, been thinking about soft IRQs. So to demonstrate this in my remaining time, I'm going to show you this script that drives this point home. So this demo will not work before kernel 6.6 because it's using the Dragon debugger and a script called workqueue_dump.py that appeared in 6.6. Dragon is a new debugger from Meta. Here we're listing for a randomly chosen work queue. We're listing from SysFS those work queues which have been exported there. Most work queues, you saw all the work queues running on this system, are not exported there. Of course, these NVMe ones and this rateback one that flushes dirty pages to backing store, these are troublesome to manage, and that's why they're exported. You actually can export any work queue to SysFS that you want, although there'd be no profit doing it for bound work queues. But anyhow, let's look at for this NVMe work queue, what parameters are settable there. There's 3 having to do with the affinity scope, the affinity strictness, the CPU mask. There's also a concurrency limit parameter, and there is a niceness. And so the default affinity scope, since kernel 6.5, I think, is per cache line, which is great. It used to be per NUMA node. Per cache line is really what you want. So let's use this Dragon debugger to query the running kernel, which work queue pool this NVMe work queue is running in. It is running in pool 16 on any core. And this demo seems maybe a little bit slow, but that's because this work queue dump produces a huge amount of information, and I'm just grepping out a little bit of it to make a point. Here we're asking Dragon to print out which other work queues are running in pool 16, and the answer is there's a whole bunch of them. And as I said, they're unrelated. Here's some DRM ones, some graphics ones, the NVMe ones, Thunderbolt, EDAC, and so forth. So there's quite a variety of work going on there. Now I'm echoing -4 into the niceness parameter, just a random value, so neither 0 nor -20. And now we'll ask Dragon, which pool work queue is this NVMe work queue running in now? And it's now running in 18. So there didn't used to be a keyworker U18. The kernel has actually created this new pool because there were no work queue pools that matched this -4 attribute. And so which other work queues are running in pool 18? The answer, as you should know, is nothing. So now this work queue has its own kernel thread. Is this a good thing? I would guess probably not. This is probably not something you want to do, but I'm just illustrating how by setting properties on the work instead of the kworker, you can actually configure the system. So I think I'm going to skip past this since I'm running out of time. I'll just say in contrast to soft IRQs, the pace of development in work queues has been kind of breathtaking. It was actually a problem for me in preparing this talk. And the new features kept coming out, and I wanted to talk about them and understand them. Fundamentally, there are performance improvements, there are new tools, and there are a lot of internal plumbing changes. And so the performance, the configurability, and the observability of work queues have all improved in recent kernels. And there even is a new tool in libbpf called WQLAT that's not even part of the kernel source that has appeared just in last month. Now, the big headline for 6.9 is that the Tasklet API, which had a use after free problem, has now been converted to use the work queue API. So you might think, oh, tasklets are no longer soft IRQs. They're now work queues. But that's not right. It's just the interface to tasklets now has changed. And to really drive that home, I show you this code, which one could call a disgusting heuristic, which now appears in the kernel workqueue.c, where it has been copied from kernel softirq.c. So the good news is all these cool observability tools that you can use to tell what work queues are doing, you now will be able to use them with softirqs. That will be really super great. However, the bad news and the good news from some point of view, since softirqs work great when they work great, is that they're still soft IRQs, and they have the advantages and disadvantages there. So the documentation for work queues also is great. It says that bottom half work queue, which is sort of what we're calling tasklets now, are a convenience interface to soft IRQs. They are still soft IRQs. But who knows, maybe there's hope there for the future. So to just summarize, soft IRQs are high rate, low latency when things are working well. In voluntary preemption kernels, they run in interrupt context, and they have to be reentrant because the same soft IRQ can be running on every core, even though only one is running on a given core at any given time. Tasklets, I haven't really had time to talk about, but a given tasklet only runs once on the system at any given time. So they're similar to soft IRQs, except now they have this work queue API, and they don't need to be reentrant. And then work queues are potentially high rate, but less critical latency. They always run in process context, and they have this remarkably sophisticated concurrency automated management system, which you can enjoy, and very good observability tools. So to wrap everything up, soft IRQs, people have worked so hard for so long to try to improve them. Things have maybe gotten a little bit better, and there's hope with this local scoped locks, which is actually called local lock BH nested, that maybe there will be an opportunity to remove some instances of local bottom half disable, the big soft IRQ lock. And with Daniel Bristow de Oliveira's RTLA, there now is some improved observability. So do go hear Daniel's talk tomorrow if you're interested in this topic. But overall, there's been a lot of frustration with soft IRQs. Work queues, on the other hand, are more configurable, more performant, and easier to observe in recent kernels. So with that, I'd like to thank Sarah Newman for her suggestions about this talk. I'll say there's a lot of resources here in these slides if you want to follow up. And as I said, you can download these. I made a whole bunch of demos I don't have time to show, but if you want to run them on your own system, you can just download it and try it yourself. So thank you for your attention, and anybody has any energy left before we all go and drink beer, I'll be happy to answer any questions. Okay. My favorite kind of beer is Hefeweizen. All right, well, it must be the end of day. Thanks, everybody, for coming, and be happy to answer anybody's questions or apologize for my mistakes in private as well.
You do know you can pin K-workers to a certain CPU.
But why would you want to?
But you didn't mention it because you ran out of time, right?
Well, I mean, you could, but given that the system...
I mean, you had a problem where you had most likely a RT task, and the worker wasn't scheduled for like seconds you mentioned, right?
Well, the real problem was that the system had lock on cleanliness, and it actually was just locked. I had a driver just lock up.
Ah, okay. Because the point is, if you would like isolate a CPU by shuffling everything away,
sure,
then you could, because there is the CPU mask feature for K-worker, you could say exclude the CPU. So even the
agreed.
unbounded, so you're aware of this. You just
Well, I kind of said that. I showed in Sisyphus there's this CPU mask.
Yes, I've seen that, but you went quick over it, so I wasn't sure if you realized it or just didn't mention because...
Right, but you're pinning the work queue, not the K-worker. That's the main point I was making, right? Because you're not using task set to pin the K-worker.
Exactly.
You pin the work,
exactly,
and you get a K-worker.
Exactly.
That's what I want to leave people with, because, oops, why don't I turn off the microphone?